All right.
Okay, so this is it. So hang on, where am I? Yeah, so we were talking there about how the importance of I suppose, what would you say, critical thinking, or well, I suppose critical thinking is more in the political sphere or something, but in terms of science, we're always trying to disprove our hypothesis, right? And that's
Mm-hmm.
important, even though, then it feels like, well, are we making gains or aren't we? Because we get to a certain point and then we have to go, well, that's not right. And then all the work that you've done up to that point is wrong for some particular reason. You have to scrap it and start again. But and that's what I find often is happening. But it's like you have all of these different roads open to you, and you go down one road. You're trying to get to a location that you can see far off in the distance. Let's say you go down one road, it's a cul-de-sac. You turn back around and you try the next one, and that's also a cul-de-sac, and then you keep trying them. So that's kind of what I was doing here. I was trying to use the ohm anamorphic universe model to measure the distance of galaxies, and basically using the Hubble constant and cosmological redshifts, and trying to pair them up with the ohm model, because as you know, we have this hypersphere, and then all the galaxies are on the hypersphere, and they're being projected onto the tangent space. And then the idea is that the higher up the sphere they are, the more distorted they're going to appear as they're projected, and so that gives the impression of redshift. So that was my initial idea, but then I started running the data to see if I could kind of, well, first I was thinking, oh, well, let's undo the redshift value, because I thought I would have to, that's like if we were to travel out to some far distant galaxy that's like 100 megaparsecs away or something, when we get out there, we're not going to observe any redshift in that galaxy. It's going to look just normal. So my thinking was that if we were to remove the redshift from all the galaxies, we would somehow get their actual position or something. But that's completely wrong, because if we have a like Earth has a redshift of 0, let's say, or something, I mean, it's not actually correct, but let's imagine it was. And then we go out to a galaxy in the Great Wall, and it has the redshift of 0.01 or something. But then if we were to undo the redshift, then that galaxy has 0 redshift. And because when we plot like galaxies, you have your what do you call it? Your right ascension, your declination, and then your third dimension is the redshift. So if they all go to 0, then everything just collapses to 0. All the points are on a single point. So this entire approach was wrong from the beginning. It was never going to work. But it was still necessary to go through this. And actually, okay, well, so this one isn't particularly good. Then I did another one, which is with a different concept, where instead of trying to get rid of the redshift, I'm accepting it. So this would be like the average length of a galaxy. And so the idea was you would generate some data and then add the average length of the galaxy to that data, I think. Yeah. And so that's what this is. So, then we transpose that onto the hypersphere, or the other way around, project it off the hypersphere to see how the projection changes the length of a galaxy, let's say. So that would give us like a better understanding of how a galaxy shifts in size, and then we could pin a z redshift to that. But then for some reason I chose not to continue with this, there was probably some error in my thinking. So here we have recessional velocities. We can figure that out from the z redshift, and then we can get the distance by just dividing by the Hubble constant. In this case, I use the value of log 2, and then, or the natural logarithm of 2, I mean. And we get this, which is a very linear graph. Yeah, in megaparsecs, and there's your z redshift, so on and so forth. So I suppose I should go back here for a bit first, so we can see this was where I was trying to rid ourselves of the z redshift, and then okay, so this is just processing so that we kind of squash the data, and then we're plotting the H alpha was basically, you know, because I had to say right, so we have these Balmer lines, the hydrogen element wavelength of this value. So in order to sort of strip away how the z redshift is calculated, we need to multiply by the hydrogen element to get the difference between the redshifted and the rest wavelengths. So that was the concept, at least. And then, well, when we plot that, we see that there's these obvious breaks in the data. And this is, I believe it's referred to as periodic redshift or quantized redshift. That's not too important, but it's just interesting to, suppose, visualize these things. And then, so we plot the first 1,000 galaxies in a straight line. So we're not plotting them radially anymore. We just plot them in a straight line. And then with this log n2 distance. So this one isn't really that accurate up to the speed of light, but it should be accurate enough. And then we get back into...
What does index means? Index, you have index there?
Oh,
what does it mean?
Index is just like you see in the other example I had megaparsecs.
Yeah.
So this tells you the actual distance with the redshift, but and that's because I was using recessional velocity and all of that. But here I wasn't quite as sophisticated at this stage, so I was just plotting without any kind of understanding of the distance necessarily. It was just purely we're just plotting. Well, I suppose this is distance in megaparsecs up here, and then the index value is just the index that this is a list of values. So each value has an index number in the list, and that's all that means really. So yeah, so this is a distance value, and I think it's kind of correct up to the speed of light, which would be way off the charts anyway. So, you know, so we have to do that correction. That happens in this equation. If it's less than 1, we do that equation, which I guess is what, the Lorentz transformation or something. And then if it's greater than or equal to 1, we have to multiply by the speed of light. And that's your answer, I think. Okay, so the problem I was having here was that I was expecting the redshift values coming off the hypersphere to be logarithmic, and then I was looking at this and I was seeing, well, here we have z redshift, we have megaparsecs, and it's very linear. So I was thinking, okay, well, I've disproven my own hypothesis, right? This isn't going to work. So I mean, it's been a while since I was looking at this, so it does get a bit confusing. This is as you go really far out, things start to climb up, and I think speed of light is around here somewhere, but I could be wrong with that. So it's just going back and forth between these two concepts, realizing, okay, well, at least I've disproven the model, and I didn't go like massively public with it or anything. I didn't do any circuit of like, what would you call it, sci podcasts on YouTube or anything, and totally disgrace myself. So that was kind of a good thing, I thought. But another thing that was interesting was like, at the time we thought the distance, the diameter of the hypersphere was 28.8 megaparsecs. Now we've since increased that to 43.2 megaparsecs, but that is a placeholder because it's nice to have a number that we're talking about, but in one way that's bad because then every time a new number comes along, it kind of goes back down the chain. I have to do all these corrections, you know, but there's still something just nice about having a value that we can work with. So because if we have the diameter, or sorry, yeah, if we have that diameter value, then we have a right angle to the on the tangent plane, and then we have a distant galaxy. So now we have two lengths of a triangle. So to get the hypotenuse, then we just do Pythagoras theorem or the Pythagorean theorem. I'm probably spelling hypotenuse wrong. Just ignore that. And then yes, so then these are the values you get from doing that, and then we can see that's linear, just nice, and so on and so forth. So I thought this was a kind of a fun concept, doing four-dimensional trigonometry with the universe and galaxies, and how we could possibly use this to find out other interesting facts. So I got the sine, cos, and tan then just through the normal ways, and then started plotting those, and then did like a 3D version where you have cos.
Your red line and the blue line, what are the difference?
Oh, here is these are the cos values.
Ah, okay.
And this is the tan value. And I assume that the sine value is, I don't know where the sine value is. It might be in there somewhere. I couldn't tell you. So because this has been well, it's been more than a month since I looked at this. Yeah, over a month. Okay, so now we get into the concept of maybe we should use the median size of a galaxy in megaparsecs. And I don't know if this value is correct, but it was the kind of best I could do just based on average measurements and that kind of thing. And so I thought, well, why don't we use some sort of distortion equation to kind of measure the length of the distortion of this average size galaxy based on our trigonometric sort of features that we've previously described. And so what I searched up something, I found something on Wikipedia called the Keystone effect, and did my best to kind of, horseshoe that into place. And I don't think the results were particularly good or interesting. To do megaparsecs. So the distortion.
You are compressing the redshift values, right? Kind of.
Yeah, well, we're trying to describe the redshift as a distortion of the. Let's say there's a galaxy and it's 100 megaparsecs away, and so it's redshifted twice to, like, I don't know, 0.1 or something. And then. And so it's distorted on the tangent space, is what I'm saying. So, and it's distorted because of a perspective shift, an anamorphic perspective shift, which is what the keystone distortion is all about. So I thought, let's just do that and plot it now. I wasn't satisfied with the results, but I cannot tell you what these results are because I've forgotten. But it might become more clear as we go along. So we just plot the Z redshifts and the keystone values, and we see that there's absolutely no correlation. So this is incorrect. Then we continue on. Blah, blah, blah. Oh, yeah. Now here I was getting probably quite desperate on some level or something. I don't know. But, oh, yeah. So this is all over the place because I think in some sense, even though I try to take away the radial aspect of the universe and just put everything in a straight line and then order everything in terms of its z redshift, we don't get a really nice curve. We just get a lot of noise, jaggedy noise, and so that's a bit disturbing, and would make you kind of question the entire basis of how ordered are the cosmological redshifts anyway, if that's what's going on here. But that's just the fact of the matter. You know, these are the index values after being sorted, so it doesn't look very sorted. So I don't know what's going on there, to be honest with you. Okay, continuing on. Right, so at this point I'm moving on to the next research, I think, really, and I've also run out of graphs that I plotted here as we got into it. Okay, so we might just be able to move on. There's probably more graphs and things there, but I think we've probably covered all of that. Yeah. I mean, I'll just run them anyway just to see, because I mean, where did I get up to? Presumably I ran these. So I'll run this. Oh no. We'll have to go back to the start. Run. And wait for it to process, which could take a while. Not too long. And there we go. No more error. So we'll just run these. And these. So hypermod. Right. So here we're projecting it onto the. Well, we're considering about projecting it onto the sphere, and that is projecting it off the sphere. Sorry. And then we get these lists of 3 coordinate values, because we're only working in 3 dimensions at this point. And then we want to get the distance. We're interested in the distances between the distorted length of the galaxies compared to the non-distorted lengths on the hypersphere. Or so the idea was, we have the non-distorted lengths, then we project it onto the sphere or something, and then project it back and see the differences. But that is logically incorrect, because that's a one-to-one thing. Whatever you project off the tangent space onto the hypersphere and then project it back, it's just going to be one-to-one, right? They're going to look the exact same. So this whole idea was, on its face, just incorrect, I guess you could say. It was just never going to work. I think I still got some weird kind of results. But yeah, but it maybe looks like we're running into a lot of errors. Right, so that's what happens with these things. I'll go back to that later. But so you've seen it. It's kind of good to maybe run through those things and have the errors, or not have, make those mistakes so that you don't make them again in future, kind of thing. And so this is it again. I think I suppose we should run these as well. Right. So this is still the same kind of terrible idea, but just done in more detail, I guess. And then we're kind of back to the original work that I was talking about, recessional velocities. I mean, this kind of thing is interesting. There's a bit of a kink or something. I suppose that comes from the difference. It's interesting that the whole recessional velocity thing is like 2 different equations stuck together, so you can really see the point at which they transition. And I mean, it makes perfect sense, I guess, from a like general relativity perspective, but there seems something a bit ad hoc about it, where you have to stick two different equations based on some parameter, whether you're under and over certain value. But maybe that's not so strange.
Dark matter, dark energy doesn't come into the picture here, right?
No. Yes, dark matter definitely not, because it's suggesting that the redshift value is not the result of any motion. Like, it's not a recessional velocity, but rather, and not even a Doppler shift.
Not a rotation curve. No
but rather
rotation.
just a perspective distortion in some sense. So yeah, initially when I was thinking that the that the redshift value should make some sort of logarithmic curve, but they actually turned out to be very linear, I was thinking, well, all maybe is not lost, because I could use some kind of refractive index either on the sphere or on the tangent plane to correct all the values nicely. But that's like that's kind of like what dark matter is, isn't it? You've got Einstein's equations, you expect a certain amount of matter in the universe or whatever, or rotational curves, and you don't get it. So you go, okay, well, we could just correct this by adding in more matter that we don't see. Not putting down dark matter as a hypothesis.
Yeah,
I think it's probably correct, and there's no reason why it couldn't be in this model. But that's another story.
Swingy, right? That was
Sorry?
Swingy who did that. Right? A person called Swingy, right? Swingy or something like that.
Is that right?
And also a lady. Yeah.
Right. Well, I'll have to look into that, because that's dark matter is a big deal. But I think, oddly enough, like whenever anything is mentioned, it always seems to fall back to Einstein. No, Einstein got it right. I don't even think Einstein even had a clue about dark matter. He wouldn't have even. And I think if you suggested it to him, he'd probably be like, "That's ridiculous," or something, because he didn't even believe. I don't think he even didn't believe in black holes or something, and he didn't believe in quantum mechanics. But he's considered other quantum mechanics as well. So the guy gets all the accolades. So let's just give him that as well. Anyway.
Schwarzschild tried to do a metric to solve Einstein equation. That's how we started getting the black hole and all that. Schwarzschild's metric. So it is.
Yeah, the
it's a way of solving Einstein equation.
Very interesting. I mean, probably very true as well.
I will kind of touch upon that in our next history episode.
Great.
I'll touch a little bit on that. How it actually happened.
Yeah, like Schwarzschild. How do you pronounce it? Schwarzschild. Like his name is sort of immortalized with the Schwarzschild radius and lots of other things. So it's not as if Einstein's getting all the credit here. So we have to be reasonable as well. So right. So if we look at let's just imagine this is the z redshift. This is the megaparsec values, and these are the recessional velocity and distance, right? So this line here. No, wait. I think this one is the Hubble version, and this one's something else. But so the idea was to run a linear regression model, or just basic linear regression models on the different results. So the one that is based on like a hypersphere model, if you like, called distance, I think, and the recessional velocity. Oh no, sorry. The distance and the recessional velocity are two parameters that we're trying to find the slope, basically, of the line, which is all we're doing here, using we're just making use of linear regression to do that, and ignore that plot and those results. And then we use sklearn linear regression because it's easier, and we see that the slope is log n2, and the intercept is 0. So that's just, we're just now chasing our own tail here. We're getting the Hubble constant by finding the slope, and we needed to put the Hubble constant in to get the slope. So this tells us absolutely nothing. But it was needed on some level. I'm not sure if that is going to appear here or not. Apparently it isn't. Maybe it's in a different notebook. But basically, you know, obviously finding the slope is important, as we'll see either in this notebook or later. Because let's say I use okay, let's just assume that this is the right notebook, and let's go with it, because I don't see another one. So here we do the same kind of processing again. Now you see we're using the old value, but it doesn't matter. It's just a placeholder. So, and also it's good to investigate these things. So then we do the spherical stereographic transformation onto the hypersphere. We have our W mod value, and now we're going to get the hypotenuse by a different method, where we are going to take, because we know where the projection point on the hypersphere is. It's at the North Pole, and then we minus it from every value in our x mod thing. So these are like, this is the x, y, z locations of all of the galaxies, and we scaled it by this value because this is our diameter value to get the mod versions. And then so now we're basically getting the hypotenuse distance from the projection point to every galaxy in the universe that we have in our data set. And then we get the distances just by using the kind of the opposite of the Pythagorean theorem. So once again, we're just using basic trigonometry, which I kind of like as a concept. And then we get these distances. So now we're getting a nice linear line, and that's all good. We have to convert to float to get over some bug in the program or something like that. And then then we run our linear regression model again, and we see that the slope is 1. So this line here has a slope of 1, and this is based on our own distance. So that's a problem, right? Or is it a problem? But basically it's saying that if this was correct, and it's highly unlikely that it is, but let's say some version of this is correct, you know, we would, if this was going to comport exactly to the parsec values that we'd see in recessional velocity and the Hubble constant, then this should be exactly log n2, you know, or 70, somewhere around there. So already we see that there's a definite difference between these two things. So we're going to investigate that difference a bit more in detail.
So this is on the projected plane?
Yes, the blue line here are the distances based on the hypersphere and the projective point and the tangent plane. The red line, this is what we would expect distance-wise and based on recessional velocities and the Hubble constant. So we can see that this has a slope of 1 and only extends to 196 megaparsecs, I think. And this one has a slope up here anyway of log n, because that's what we set it as, and it goes much further. So all the galaxies in the universe, according to the own model, are all squashed in here, but here they're like spread out all the way to 25 billion parsecs, or so gigaparsecs. So we can see there's an obvious difference between these two results. So this is exciting in one way because we have entirely new values, but there's a problem that we don't actually know the distance to the projected point in the 4th dimension. Like we're guessing now that it's 43.2 megaparsecs, but even those distances, right? If we're using our we're using what to measure that? We're using the revised support vector model, remember? But that was predicated using the distance to the using the recessional velocity distance, if you like, or the Hubble distance, or whatever it's called, to the Great Wall. So we, you know, no matter what we've done here, we have this implicitly in there. So we should reconcile these two to see if, you know, if they're correct, because we're using this system as the basis. So we need to make sure that this system actually conforms to this one in some way. Otherwise, it's meaningless, because and it's better to do that, because then we get a value for the diameter based on the redshift value of the Hubble distance.
Conventional distance means measured. I mean, actual telescopic measurements.
Well, there is no actual telescopic measurements. There's only the only distances that we have telescopically, let's say, in terms of parallax shift, they can only be measured within our galaxy. So anything outside of our galaxy, as far as I'm aware, and certainly anything close to the Great Wall and beyond, are they're all based on redshifts. So all we have to go on for our distances are the redshifts. So you see how flimsy this entire concept of the Hubble distance really is. It's fascinating. Like when we put it like that, it's pretty fascinating. But that's not to say that the model that we're working on here is any better, because as I've said, we don't know the distance to the projective point in the fourth dimension. So that's an X value. And that means that you can put any number in there within reason, you know? Obviously, it has to be bigger than some value, like let's say 28 megaparsecs to
like a fudge factor.
Yeah, so there's some fudge factor there, but it's still enormous. Like it would, you know, so you could have like it, and it's useless, because such a big range will never hope to satisfy anyone's interest or curiosity. Okay, so here I believe this equation then, or this function, I mean. Yes, it is. This function essentially kind of solves the problem that we're talking about, because it takes the ohm distances and matches them with the conventional distances within an error, okay? And that gives a result of this value, which is in megaparsecs. So we're talking about this value here is 4,218 megaparsecs, or 4.218 gigaparsecs. Now, there's a difference though. Yeah, they don't lie on the same thing. So I actually projected that the value would be, I don't know if that's still, okay, it's not in this notebook, but I projected the value would be 4,320 megaparsecs. And so I conjecture that the difference between these two lines would bring you to 4,320. But I never actually solved that to, I don't think I did, to such an accurate measurement. Oh, things are slowing down here heavily. We're getting into, actually, I probably shouldn't have let that run for so long. Because, you see it's getting closer and closer, or is it?
So you are changing the factor or something like that?
Yeah, the factor is going up, you see. So I didn't realize that was running in the background while I was talking, so that's probably going to be an issue.
Kind of like X factor, huh?
Well, yes. So this is the diameter then of the hypersphere, right? 4,237. It's getting closer to the mark. So now we're getting the diameter of the hypersphere as it would be if the Hubble distances are correct, which is interesting, because 4,320 megaparsecs is just, what is that? It's just 100 times more than the value that we currently have, like on the button. So that's kind of interesting. Okay, so yeah, I don't think it ever really converges. Wow, that's a lot of graphs. Oh, it does.
Of variance at the beginning. at the near the origin, there's a lot of variation.
Oh, down here. Yeah, I wouldn't worry about that though. Yeah, that's a good point though. Well spotted. Yeah. Well, like I said earlier, that I feel there's a bit of a fudge factor, or not a fudge factor. I didn't use that word, you did. But I feel like, you know, there's something wrong where you have to, if you have to stick two different equations together, it feels a bit like you don't know what you're talking about. So you just go, okay, well, it doesn't work above this value. So, and I don't even understand why they say it doesn't work above that value, because when you think about it, I mean, when you really think about it, like if, you know, they're saying, oh, well, we're getting recessional velocities that are higher than the speed of light. But that's completely okay in the Big Bang model, isn't it? Because space is expanding. So something can be the further away it is, the faster it appears to be expanding. So it can appear to have a redshift velocity that's far in excess of the speed of light. But I assume that's true anyway. But I'm sure they have their reasons for this, and it's all well worked out within that logical.
With these adjustments right on, rest of the things are matching perfectly.
Yeah, like I said, yes. So that's what we're trying to get. Like we're not concerned about this, because this bit here and the other red line is all based on recessional velocity, but our model doesn't have and so based on the universe is expanding, space is expanding, but our model doesn't have that, so we don't have to worry about this issue. I don't think, because nothing is moving, right? So it's not about speed. So the speed of light isn't an issue. So we can just go straight through this line. It's no problem. And as you see, they begin to match up pretty well around the expected value, right? 4,320 megaparsecs. So I deem that roughly to be the size of the diameter of the hypersphere if the values of the Hubble distance are correct. And I would argue that they aren't. Now, we already have an error here, so I'm assuming that this notebook is dead. So I'm going to have to restart it. And I think it's completely dead. Yeah, we're going to have to restart. I might as well close this one because we're done with it. So close that one, or shut that one down, and shut this one down as well. And then we'll close it and leave page. Okay, so now we need to reopen this one. Hopefully everything will work. So at this point, I was like, right, okay, we now have the answer, right? Because our original value, this value was based off redshift recessional velocities anyway. So, and now we've shown that in order for the hypersphere projections to conform to the Hubble redshifts, the diameter of the hypersphere needs to be much bigger than this. So this value is wrong, and our other value is also wrong. But we actually have to be very careful here, actually, because I don't think we have measured the diameter in this case. What we've done is measured the radius of the hypersphere. Okay, so that's a bit strange because, well, maybe it's strange based on other information that comes up later. I can't remember why it's strange right now, but I'm pretty sure that this is the radius value, which means that the diameter would be twice the size of that. It would be like, I don't know, what is that? 8,640 megaparsecs or something. Okay, so those are our values. We're going to skip running that. We don't need to run those. And then we get our, or do we need to run that? Let's try. So there's just another linear regression model. I think these are just, yeah, these are just smaller versions of what we've already seen. So conventional distances minus the ohm distances. Obviously, that doesn't give us very much information. This was just other stuff I was working on while trying to figure out the main thing that we discovered. And I don't remember what this is. So you can see there's the redshift distance.
A lot of noise.
Yeah, it's interesting. I think this is the reality of the situation in some way, and this is the idealized version. But we can see that
because of distortion. Is it because of the distortion that is showing that?
This might be, again, remember where I mentioned that there's some extreme chaos or irregularity in the redshift values. Remember I showed that in a different graph? I think that might be just this repeated again in a different way. But what we've done is...
One of the things that, the stars are forming, but they are also changing, right? I mean, they become black holes, all that. Probably that will affect the redshift, right? What's going on in the galaxy, the dynamics going in the galaxy, inside the galaxy will affect the
redshift. Well, yes, they do say that because, like, we have these things. What are those things that Holt and Arp discovered? The anomalous redshifts of galaxies and quasars. So basically, Holt and Arp discovered like bridges between the galaxies and these quasars, and the quasars are highly redshifted, so they should be like the furthest objects away from us. But he noticed that they actually appear to be sitting on the same plane as some of these galaxies with very low redshift. So in order to explain these high redshifts, astrophysicists have claimed that, there must be a black hole sitting in front of the quasar, which is causing like a refraction of the light, which makes it look further away. But the idea that would happen, because all quasars are enormously redshifted to bejesus, So
warping the space-time.
Yeah, but well, I suppose quasars are black holes, so that's what they're considered to be. But I think in order for them to appear more redshifted than they are, there has to be something nearby them, which is causing a distortion. Yeah, but
the other type is a magnetar, right? Magnetar.
In order for that to be true, yeah, there needs to be a companion black hole beside all of these quasars in just the right way to produce the exact same effect on all of them. Is that what they're suggesting? Yeah. Because if so, that's ridiculous. So I think we can sync that one right now and say, no, that's not happening. And if it was happening, why aren't we seeing it with just ordinary galaxies as well? Although technically, how would we know? But basically what I think cosmologists are saying is that these kinds of redshifts that we're talking about, large redshifts of galaxies far away, can only happen because they are so distant from us, and that there's so much space, and the expansion, the cumulative expansion of space off to their locations creates the redshift. So it is in no way a local thing that should happen within the galaxy. Because it has to be a kind of not a global phenomenon, but I guess a far field, to borrow that phrase in the wrong sense of the word, probably. But I'm sure you could talk about far field and near field gravitation.
Smearing effect.
Sorry?
Smearing, like a smearing effect or something. smears the entire.
Yeah. That's what they're saying, because as the space expands, wouldn't it? It would. I think they say it affects the wavelength of the light, so it expands the wavelength. Anyway, there's a lot of weirdness that can go on then, because I was talking to a colleague of mine, and he said that if you think about, like, he was looking at the results that you get when you plot all the galaxies and how they appear in these giant concentric circles around the Milky Way at the center. And, like most astrophysicists or cosmologists working in the field today, they assume that what they're looking at is somehow an artifact in the data or something. And then they choose statistical methods. So they take large amounts of galaxies way out to like real far redshifts. And then they use statistics to show that, well, actually on average, those circles don't exist, but they do exist because we're looking at them, they're like quite obviously there. So you can use statistics to prove anything you want, and to remove things. And especially because we don't accurately know the distance of these far objects, particularly like if a lot of these far objects are quasars, and the quasars are actually not as far away as we think. They're actually sitting somewhere inside these rings. Then all those measurements and that statistical analysis is therefore bunk, which is pretty obvious anyway to anyone. But he came up with an interesting idea anyway, that it was that the reason why the rings are there was because that light coming to us is from when the universe was younger, so all the stars were closer together or something like that. But if you think about that logically, like from a Euclidean geometric perspective, such a thing is impossible. Like he's essentially saying that we only appear to be at the center of those rings because everything was closer together further back in time. But then if we were to go out to one of those galaxies and sit on a planet there and look out into space, then we would expect to see the same thing, that Earth would now be, we would now have a great ring around us, and the Milky Way would actually now be part of that ring and not where it is. You know what I mean? So that would break all laws of, like, Euclidean geometry would just go out the window. You know what I mean? Because it would be like, I'm sitting in this chair and I have a ring of people, 10 people around me sitting in different chairs. But from the perspective of each of those people, they're sitting at the center and we're sitting around them. And breaks all, right? Doesn't it? Yeah, we would have no concept of distance anymore.
Reference frame. It's the problem of the reference frame.
Yeah. Well, okay, so maybe because you have a greater knowledge of general relativity or special relativity or whatever, maybe there's a way around it, but I don't think there is a way around this. And I don't think that cosmologists would agree, because, cosmologists don't agree seemingly that the universe is inhomogeneous. They think it is homogeneous, that no matter where you are in the universe, it looks the same. But we know that's not true, because if you're sitting at the center of these rings, like if you're in the Milky Way, it looks like you're at the center of these rings, and there is no way for that to be homogeneous in any sense, because you cannot be at the center of rings like that without breaking Euclidean geometry. And I believe, if I'm not mistaken, general relativity isn't based on Euclidean geometry, is it? it's kind of more based on Riemannian surfaces and tensors, but those are, those things are just talking about bending of space. That's a local effect of a planet sitting in the fabric of space. So it's not going to be able to deal with what we're talking about, which is a large scale weirdness. Anyway, the the point was completely wrong anyway, because in order for something like that to happen, you need to be like really far away. You know, like this idea of the universe, seeing the universe at as it was close to the beginning of the universe when the stars were all close together. You need to go like really far back. You need to be, your look at distance is really far. You're talking all the way to the CMB, I think. So the point is that basically everything in our local environment is pretty much contemporary to us now in the universe. It is not, we're not looking back to the beginning of the universe if we're just looking to the first wall. Like that's basic, that might as well be happening right now. You know what I mean? What we're seeing there, because it's so close to our time frame. So that whole point is incorrect, but still a far better argument in some respects logically than, even though it breaks all logic in known logic in existence, still better than the statistical argument put forward by cosmologists. But it is also refuted by many arguments made by cosmologists. So, you know, it's by no means like any kind of slam dunk victory or anything, and that's not what I'm suggesting. So yeah, so what's the next step here is that, so it's all the galaxies being close together. Oh yeah, but if you continue that logic, then, I mean, if we're looking really far back in time, yeah, and we are saying that the further, like using the JWST, I think it's called, yeah, like the further we look back, let's say we're looking back, I don't know, like, I don't know how far we're looking back, 30,000, 300,000 years before the Big Bang. No, that's wrong. I think that's the cosmic microwave back radiation, but maybe like 100 million years or something, 50 million years, something like that. So we would expect the universe to be denser. Everything should be closer together. It should be hotter, denser, brighter the further we look back. But we don't see that. Everything is dark, pretty much, and everything is spaced out, and everything is old, you know? So we have fully formed galaxies like pretty much straight after the Big Bang, they're saying in cosmological terms, something like, you know, within 100 million years or something, or even less. So it shouldn't be possible. And they're much bigger than the Milky Way. So, but this is the issue, right? So if the universe was smaller, hotter, and denser the further in time we go back, and yet the further we look out, that area is bigger than anything we know of. That is like the biggest area you can imagine, because it is the outskirts of the universe. So how does that comport then if space is expanding as well? So then that's going to even create more problems for your theory, because now what's happening to the light, it's also stretching in all sorts of ways that we can't really properly fathom logically. But if we do attempt to fathom it, we say, okay, the light is stretching, which means its frequency must be increasing. Is that right? Because of, to keep the speed of light constant.
If it stretches, the wavelength is going to increase. The frequency will decrease, kind of. Decrease, I don't know.
Right. Thank you. Yeah. See, this is my yeah. That's right. I always get muddled up between these little details. Really trip me up. Thank you, though. You've got the details down, which is that's why we're working properly here.
Yeah.
So yes. So but what like, does that even matter then, that the frequency would have to be increasing? You know, I mean, okay, maybe that could even be a separate issue that we'd have to discuss later to really chisel that out. But it seems like they neglect that part, because they're saying that the further back you go in time, the further you look back, the more time dilation is out there. And so we're getting the time dilation because of the wavelength increase. But that shouldn't matter if there's a thing called the constant speed of light. The frequency should increase to make up for that. So we should see no time dilation. But perhaps I'm wrong on that. I'm not an expert in that field. So that would just be that's just my initial thinking on it. But I think worse is this idea of, you know, and they explain it by saying, well, light is a scalar, right? Okay, so it's expanding, but it's somehow keeping the same image. So it doesn't the, you know, the more it expands, it's kind of like fractal or something, and it stays, there's no distortion. That's why when we look out into space, we're not seeing everything clumped together. It appears spread apart. So I would have massive problems with that idea as well. But I do have sympathy with the concept that light is somehow fractal. And I think, not that, I don't think they're saying that, because I think they're quite boring in a lot of their opinions, and they're.
I think what I'm coming up.
I mean, you know, I mean, sorry to interrupt you there, Rajan, but you know, like, they are saying some pretty out there stuff. Okay, space bending, time dilation, these aren't boring concepts. Dark matter is not boring. You know, expansion of the universe, Big Bang, black holes. These aren't boring concepts, but you know, sometimes they can be a little bit too conservative, and then that's certainly been the case in, you know, in the past. You know, you know yourself. So, but at the same time, when it comes down to it, and their theories are on the ropes, they are open to. Then they open the door and say, okay, well, what crazy idea have we been trying to keep out? And I was like, oh, multiverse. Oh yeah, you can come in and play, and you know, we'll do something with that. Okay, that's pretty cool. But you know, I think, and I suppose being conservative is a good thing in physics as well. But and certainly if you don't have like a very good reason to start talking about, although I think they already, based on their own admission, they would already have to have a good reason to talk about some sort of fractal element to light. And maybe this is actually something that is in the textbooks. All I know is Laurent Notel did some work on fractal. What was his scale relativity? So he's saying that relativity is somehow true on all scales, not just at all distances or speeds or whatever. And so his theory was that, you know, it's a kind of a fractal theory that as you go, doesn't matter what size you're at, it's going to be true at no matter size. So, but I think scale relativity is basically rejected. But I'm not here to fight battles for scale relativity, because I just have no interest in it. But it's just the idea of, like, you know, you rarely, I would say, if fractals are a big deal in mathematics, and they're also a big deal in other areas, and like in like subcultures as well, to do with like what do you call it, psychedelic kind of subcultures. But it doesn't, correct me if I'm wrong, it doesn't seem to have made its way into astronomy or cosmology in the same way. And it's certainly not as prevalent. In fact, I would, you know, if someone tries to bring in, like, what's that number, phi, you know, 1.618, you know, it's kind of like, it's considered woo, like, to bring it up. Or the golden mean is like, everything is based on this spiral, or like everything is a fractal. They're like, I don't think cosmologists really want to go there unless they have like good evidence to say that that is the case. And certainly when you look in the universe, you don't see any fractals really. I mean, you know, I don't see them. So it seems reasonable to keep them at bay then, or just,
maybe a local phenomena, you know, fractal may be a local phenomena.
Right. Well, in ferns and things like that. Okay, so yes, so this red trace is Z mod. So it is the Z values, the redshift values that were multiplied initially by our circumference distance. Yes. No, not our diameter distance. And then they're just plotted. Oh, wait a second. Okay, so it's our modified Z's by our normal z's, by our normal redshift. Now that is a very, I don't remember doing that, and I don't know why you would do that. But I think the effect is interesting. Like if we were to zoom in here, it is chaotic, but we see that there is it's conforming to this line here very nicely. So that's probably because this is in there. So that's not really that important anyway, so we'll move on. Right, next. CMOD distances. These are just the data types. Now, this is a server.cast jobs. So this is from SciServer. And I think we don't need any of this. And we just get the image from the SciServer of a galaxy. And I think it says the... Yeah, well, I don't think this really matters too much. Okay. Is that it? So, yes, I think that is it, Rajan. That. We're now up to date on the ohm distances. However, the story doesn't end there, and it will go on. I've figured out a possible way to solve the problems that we're talking about, and to find the value of x, the diameter or the radius, because there was a bit of a confusion between the diameter and radius, but
that's the hypersphere, right?
Yes, diameter of the hypersphere. So there is a way of doing it, and it kind of involves going back to the other method that we spoke of, which I think was this one, where we're talking about the average size of the galaxies, and so it's going to be more in that line. We're talking about the difference between that which is not redshifted and that which is, and that value, once that value conforms to the z redshift, then that will give an empirical value for the distances, and that's no longer based on redshift. So no expansion, no longer based on velocities. So no expansion, no issues with speed of light anymore, no piecemeal equations. But we're getting ahead of ourselves because I haven't done that. So like I said, I'm trying to get to this point that I see off in the distance, and I'm going down all these avenues, and at each point I'm getting blocked. Some cases we're getting the answers we want. We know the size of the hypersphere from the conventional distance, Hubble distances. So in some sense, if the conventional model is true, the ohm model is not true. So finding that distance is irrelevant. But it's still fun to have done it. And if the next path or the next few paths, if one of them proves to give us the actual value for the hypersphere, then great. If not, then project is put on hold until such time that we do get those values, I guess.
So you have to change the ohm model. You have to kind of rework the ohm model, or what?
Oh yeah. Well, isn't that what the whole point of me talking about this was, to point this out? I thought I spent a long time.
You're saying the original hypothesis was wrong. The null hypothesis based on that.
The one based on the support vector model, machine model, the one that we did, with the support vector. Those did, Well, that's wrong.
Okay,
It's wrong.
That's wrong.
Yeah, but it's off by
the SPM model is wrong. The support vector model is the machine is wrong.
Yes and no. I mean, actually, that's a good point. And that raises another issue, because I'm glad you brought that up, because yeah, you'll recall that we did work on the, is this it? Oh, I've got this one as well. Remember, we were trying to fit the inscribed hypercube into the hypersphere, and then project that onto the galaxies. Well, I did. Excuse me. I'm sort of. Are you able to hear me?
Yeah.
Hello?
Can you hear me? Can you hear me?
Where am I? Oh, okay, good.
Can you hear me?
Yeah, you were kind of you were roboting a bit there, you know, but I can hear you now. Yeah, okay. Yeah, all good. So yeah, it does seem like there's more to this than possibly than I might be making out. Everything might not be as clear cut as I'm making it, and this is something that we'll have to deal with, figure out what the truth is on the matter. So there's a wireframe of a sphere. Now, what I'm attempting to do is create this wireframe, but for a 4-dimensional sphere, hypersphere, so that we can repeat the previous work with the inscribed hypercube, but actually using a sphere this time. But I don't have the proper equations, so I'm running into some difficulties, and the end result is this shape here. So this is basically the best I can do at the moment. Yeah, it looks cool, but it's not, as I said, it's probably not right, but maybe it's right enough that we can make some general statements about it. It's pretty cool. It kind of goes on forever. But so let's say this is the outer sphere of the hypersphere projected, and this is the inner hypersphere, and ignore the rest of them. I don't know what they are. Well, if that's the case, then this is a hypersphere projection that we can then project inside the universe. You know, the 3D version of the universe. So I think I have to run these scenarios for this story. And then using that, but you know, this is something that we constantly have to be careful about what we're talking about, because if we're basing any distance at all on the Hubble distances, then our model must conform to the Hubble distances, you know? And we already have the value for the Hubble distance, for the diameter of the hypersphere based on the Hubble distance. So in a sense, this is a bit redundant. But, right, so going back to the, to trying to inscribe the hypercube into the hypersphere, I had to use some correction factor for some reason, which was 80.82, and that needed to be multiplied to this cell and then stereographically projected back. But then when we get the results, you see that we have some values are 0.5 redshift, and so those are the inner cube as well as the inner sphere, and some of them are infinite. Basically, they are infinity, like this value, infinity minus 0.5 redshift. So basically infinity. So we're never going to get the value for the outer hypercube based on this method, meaning that this method is just probably wrong, you know, because I'm expecting that is, you know, not all the way out at infinity. It's not distorted to that degree. But if we zoom in here to the center, there's our inscribed hypercube, but it's only the inner cube. Now, my theory, right, is that if I zoom out here, you see the way it gets dense and all the galaxies sort of, we get this ring and we get these lines at the top and bottom. So my feeling is that the inner sphere of the hypersphere is perfectly visible in there. See it there? It's like, it's this. It's much bigger than that little cube in there. So that's the inner sphere, and this is the outer sphere. That's my feeling. Or maybe this, but something along those lines anyway. You know, this maybe could be the inner one and this. So it's hard to know really, but I think the main point...
Yeah, botched out. Kind of like botched out.
I don't know what that word means, botched out.
Botch means it's kind of a smearing. I mean, it's kind of a, you know, becoming a little vague.
Oh, yeah, yeah.
You cannot really discriminate, or you cannot really resolve the actual dimension or the size.
It could be that way. Yeah, it could be vague. Yeah. No, you're right. I mean, this is it, because he used to say, right, those he used to say that those concentric spheres don't go on forever, right?
Yeah.
And much like our failed hypersphere model here, you know, if we put this one at the center, then maybe this one will match up, you know, or this one, you know, we have lots of options. But that's obviously not how this works. You know, we're not allowed to do that. So here we go. This is us putting the hypersphere in there.
The wire model.
Yeah. So you can see it sits around the big one, and it's got the spikes on the top and the bottom. And then we zoom in, we see that the other one also sits nicely inside the inside that space we were talking about. So this appears to be...
It could be an open universe, you know. We are trying to put a window to it, or bound to it, because actually it could be unbounded, you know, the actual universe unbounded, but we are trying to see.
Oh, I understand. Yeah. Well, I mean, the actual universe is unbounded. I mean, look, it's stretching out to infinity.
Yeah, yeah.
But the hypersphere is a sphere in 4 dimensions. So it has to be bounded, because a sphere is bounded. Right? So what we're attempting to do here is to say, well, if there is a hypersphere, and we want to project the hypersphere from 4 dimensions into 3 dimensions, and we want it to line up with the great walls of galaxies and with the geometry of the local universe, and that is what we can do that. But what I cannot do then from here is to say, okay, well, how far away is the circumference, let's say, of this sphere from the central point where the Milky Way is? Or how far away is this latitude line from the Milky Way? Well, what am I going to use to determine that? Am I going to use recessional redshift velocity? Because if I do, then, you know, this is giving me a value of 0.03, but that can't be right, because if I go in here, I get a value of 0.1, which is higher, and the redshifts in here can't be higher than the redshifts out here. So you know, we can't base it off what's being plotted here, because there seems to be a certain amount of chaos going on, which shouldn't be the case. So that could be definitely shouldn't be the case. So that this could definitely be my error somehow, but I don't know what that error is. But even if it was correct, right? Even if these values did line up as we imagined they would, we're still basing it off recessional velocity. And as we've already determined, in order for the own model to match the recessional velocity, this hypersphere has to have a distance of 4,320 megaparsecs, and that is either a radius or a diameter value. I think it's a radial value. So that would imply that these things are a lot further away than they appear somehow. But yeah, and I think that would probably conflict then with the distances as determined by actually, I'm fairly certain it does conflict with the redshift recessional velocities. So we get to a point where there's just a lot of contradictions, and so we cannot say anything about the sizes of these objects, which is why we need the new method that I'm going to propose, but that I haven't even begun doing yet. So we might tackle that another week.
Is it still a four-dimensional hyperdimensional sphere or something else?
This is the projection of the hypersphere into three-dimensional space.
No, the new model.
Sorry. Yeah, no. When I say new model, I mean the new means of confirming the model, and determining the size of the hypersphere, and all of that. It's going to be actually it's not clear whether it's possible, because in order to do it, we need to talk about this value here, which is the wavelength of the hydrogen element. So that is 6,562, what would you say, nanometers or picometers? It's small, angstroms anyway, is it? It's like tiny. Or is it in a Hertzian wavelength? No, it couldn't be Hertz. Hertz is frequency. Anyway, whatever this is.
-8, right?
What is it? Oh, small.
10 to the -10 to the power -8 meters, which is angstrom.
Right. Okay. Yeah. And angstrom has another. You can use angstrom has another a name. It's like
nanometer.
Yeah, it's like
angstrom is like 10 nanometers. 10 nanometers.
Okay.
Yeah, 1 angstrom is 10 nanometers, I think. Yeah.
That's right. Yes. Yeah. Spot on. Okay. So now, right. So this is the value that we have in our lab. Yeah, in the rest frame of our lab on Earth.
Yeah.
And we want to talk about a z redshift value way out here. Like, let's say this is hundreds of megaparsecs away. And then we're saying, well, what's the value out here of that nanometer wavelength? So we're talking about doing extremely small mathematics and extremely large mathematics all at the same time. That would be the only way to process this information, and that's going to be either impossible or very difficult, because I'm not a mathematician in a trained sense. So I don't know if you have any weird or crazy ideas on how to achieve that. If there's some
right now what I'm coming out is like quantum cosmology talk about. I'm coming out something called quantum form, which I'm going to present. The history itself is there. The history helps us to dissect these things very carefully, history of physics. So that's a good thing, because whatever is happening that time only we are talking about. So now, as the quantum thing developed, eventually, the Planck thing came into being. And I believe that it's more correct, because the conservation is very important. We know the conservation of energy from the thermodynamics. Then I approved the conservation of time from the tensor time, especially tensor time. So if we combine the energy and the time, we get a Planck, the Planck, constant. Okay. And that's conservation. That is I'll call it total conservation. So from there, I figure out the matrices, and it seems to be like quantum form. The quantum form is keeping the conservation. See, how is it keeping physically? How is it keeping the conservation? The electromagnetism is conserved. Gravity does not follow conservation law. This is something I have come up with. We'll consider later gravity, but the electromagnetism follows
Yeah.
conservation. It means the light is traveling, it can travel all the way through the universe, right?
Yeah.
So there has to be something that is allowing that, and that is the quantum form. Quantum form is just a fluctuation, and the light can pass through that. It
Okay.
replaces ether
Well, I
or
mean,
vacuum.
some people suggested the quantum foam existed. As a
Ah,
solution to some problems. I think, or
yeah.
I think rather it was kind of like a block. It was. I mean, was it kind of there in a way to say that time space is granular or something, and that space time is granular, and that's the reason why you can't unify quantum mechanics with relativity. So,
Ah,
but then there was all these kind of theories about like tiny wormholes and stuff in the quantum foam,
yeah.
and then I think experimentalists, a good few years, like decades ago now, looked into it and they developed an experiment to look for the quantum foam, and they said, well, if it exists, we're going to expect to see these results, and they did it, and they didn't get it, so they said this just proves quantum foam. So, but I don't know about that. I mean, you have 0.10.
I think the problem is I think they're mixing gravity with electromagnetism. I think you cannot. You have to separate the two.
Oh,
That's my feeling.
what about
So if
the
you
whole?
separate,
Isn't the whole Wait, isn't there a big project though to unify all the fundamental forces in the
yeah,
universe?
but I think right now, because the conservation applies only to electromagnetism, it doesn't apply to gravity. More equation of motion is a lot more. See, what are the final things I'm coming up? This gravity is not a force. It's probably like a gradient. And
Oh
that's a
well,
hard thing to chew upon. It's a
yeah, but I mean
gradient, like temperature.
that is the basic fundamental take home of general relativity. Gravity is not a
Yeah,
force.
yeah.
But I would
It's
disagree.
like a
I
gradient, like
personally, I
temperature.
mean, yeah, okay. If we accept general relativity, I think then that's probably
Ah,
true. I think we also probably should accept general relativity. So, but
I don't know whether,
I don't like general relativity. I only accept it
yeah,
begrudgingly. I just don't like it.
conceptually very true.
I think it's a
Yeah.
mess. It's a total mess. But
No, no, no. I think we can use it only in a second way. In a limited,
yeah.
restricted way, you can use the general relativity.
And then it's
You
great.
cannot just,
It's pretty cool. I really dislike the mathematics that they're using for it though. It makes it so
you have to
elitist.
rearrange.
It's so difficult to
Yeah,
get into, and but apparently, if you want to use those equations, um, and calculate these time dilations and all of that for whatever
no, I
reason
don't
you
believe in time
wait.
dilation.
No. I'm not saying
Those are,
you. I don't mean you personally. I
yeah,
mean if one wants to do it.
yeah.
Uh,
True, true.
the way you do it is you just have like in the back of one of these statistical log books or whatever, there's a lookup
Yeah,
table that you use for your equations. So,
yeah,
all of these fancy, complex tensor things that you
yeah,
see, when you're talking about theoretical physicists working on problems and applying general relativity to it, that's another, you know,
yeah,
ball game altogether,
yeah,
probably. So,
yeah.
I think, but that's where I find it's definitely not. I think it's maybe structured for minds who are around in maybe the turn of the century. Who, I mean, what were they doing? They were reading Chaucer and drinking.
Oh, yeah.
It doesn't matter what they're drinking. But you know
Sherry,
what I mean? They were different. They're spending most of their time
champagne.
outdoors and like whatever, writing with
Yeah,
like.
drunk.
It was just a different time. So
Like,
I think
yeah,
personally, it's not something that I gel with. I prefer something a bit more futuristic, or a bit more,
Concrete.
yeah, a
Concrete.
bit more comprehensible as well. Like this is quite
Yeah.
comprehensible, I feel. So it's what I'm interested in.
Yeah, I agree. I mean, I believe in the physics. So I'm saying that you have to be very careful in using the general relativity. People kind of roughshod, that you can use it in a certain sense, and that's it. General relativity. You cannot say, okay, that is the whole story. You know what I mean? So I
Yeah,
think that's where the people made a mistake. You know, I mean, some of the concepts are pretty good, but actual how do you apply them is something different. So that's what I say, that because of course we know there is a problem with meshing up when you bring the quantum general relativity to the quantum level, everything blows out. The same way quantum, if you go to the general relativity, it blows out. So there is a mismatch between the two, and that's because the
yeah,
realms are different. Like you say, the granular aspect of space time may be one of the reasons. The
yeah,
discontinuum, what I say with the Emery Taylor is the discontinuum aspect makes it all, totally, it blows out the whole thing. So that's what we have to consider. See, I found, like said, like how Riemann, for example, right? Riemann set a function, and also like the what you call, you brought out about the integers, right? The integers coming.
yeah,
I found a relationship to the continuum where you have the error function, and you apply the, what Riemann argued is what, if it is true for all the numbers, continuous numbers, which
yeah,
means that then it should be true for, because integer is a subset of the continuum, right? Continuum. So if it's true for the continuum, then it should be true for the integral also, because the integral numbers or digital numbers are
yeah.
subset of the whole of the entire number system. So that's how he argued, but he rightfully said we have to still prove it. So that's why he called Riemann hypothesis, and we find that the zeta function is still valid because of that reason. You know, so
Oh, are you talking
it's
about
the argument of
the Riemann
huh?
conjecture?
Conjecture. Yeah,
Isn't the
same
Riemann
with Fermat. Yeah,
conjecture about prime numbers in the, or no, it's about the number
yeah,
of zeros on the critical line
yeah,
in the Riemann zeta function.
yeah,
Whether, yeah, whether they're all on the zero critical line or something. And
yeah.
if you can prove that, you win like $1 million or something.
So
Well,
I'll
I'll
come
tell
in
you what,
about.
Rajan,
Mm,
that's interesting.
yeah,
I'm interested in the Riemann zeta function. I've done a little bit of work on it, as you mentioned, and especially in relation to the hypersphere and stuff. So there should be more coming on that in future. But um, yeah. So, well,
yeah,
how long? We've been going for an hour and a half. Do you want to take a
yeah,
short break?
yeah. We can,
Yeah.
about 10 minutes, 10 to 15 minutes. Okay,
Great. Okay, get a
fine.
drink because I'm parched. I've been doing a lot of talking. And then when we come back, we can discuss other
Yeah,
things. Cool.
okay, okay.
Okay.
Thanks. Yeah, we'll see you in a bit. Thanks. Are you there? Hi, Christopher. Are you there?
Hello?
Hi.
How's it going?
Is it okay to continue now?
Yeah, it's good. Not sure how to can you can you add me to the stream there? I don't know how to do it.
Oh, okay. Let me see. Oh, you went. Okay.
Oh no, wait a second. Sorry, there we go.
Oh, yeah. Okay. Yeah. Okay.
Ah, yes.
All right.
Okay. So, well, I think so. The title was "Dimensions of the Hyperspheric Universe and Rank Tensor Time." So we've covered dimensions of hyperspheric universe pretty
Yeah.
well, not conclusively, but
Yeah.
extensively. Is the word I was looking for. So, with regard to the rank tensor of time, I see you have some notes there.
Yeah. I think yeah, I'll present some, but also I want to present the history of physics. I have some PowerPoint after this. We probably will get off this, and then I'll just want to go with you
Oh
whether
yeah,
it's okay.
yeah.
Like
I'm
last
sure
time,
it's fine. Anyway, the last one was great. Enjoyed that.
Let me check. I had a lot of things on that, but I don't want to present it. I want to be careful in it's ongoing things. A lot of things involved, but we are simplifying it. So that's what I'm trying to do about the rank tensor. So, just brief on that. I was watching our earlier videos, some corrections. I think I made one mistake there. I just want to correct. See, we are talking about, so probably I would start from there. Um, yeah, for example, this one was one of them. Can you see?
Yeah. Oh well, kind of. It's a bit pixelated.
How?
You need to up the. It's coming through gradually, but it's a bit blocky or something.
Let me see.
Yeah,
Let me see with this.
it's just a bit low,
Sometimes
right? Because
the way I put it, sometimes it matters.
yeah, I think it does have an effect. But even so, I think maybe the resolution of the camera is a bit low. If you can, is there a way to increase the pixel
Yeah,
size?
yeah. I also see in one screen I have it's clear. The other screen because I have two screens
Ah,
to figure
well,
out.
the other
The
screen,
other screen kind
the
of
other screen
yeah,
you're
kind of
watching,
hazy.
that's coming through a bit clearer there. Don't move it.
It may take a while to clear up
Okay, there
if
we
there
go.
is
We'll have
some.
to make do with that. So I see matrix element for
Okay.
16. Okay, go ahead there,
Yeah.
Rajan. Take it away.
Yeah. So one mistake, I think you may have noticed that this should be I don't know whether you can see that. Okay. I don't know why it takes a little while to clear it.
Well, once you get it, just don't move
I,
it.
if we see it clears by itself. Yeah, a little bit clearer, right? Okay. It's not as clear in the other screen. It's very clear, but in the
Yeah,
other in what you see, it's not very clear.
yeah,
That's
very
it,
true.
yeah. So I can see both of them. And I can see why they are sensitive to something. I don't know the air. All
I don't know
right.
what it
So
is.
here I talk about 4D. Can you see 4D space? Oh, it's kind of botching. Kind of. I don't know what's going.
I
What
don't
it
think
is
you can.
doing.
I don't think you can move at all. If you just yeah, you can't move like and point to things. You need to zoom
Yeah.
out.
In
I
the
think.
other one, yeah, it's clear. No, why is it doing that? Okay.
Hmm. Okay,
Let
that
me
might,
get off and get on. Maybe,
yeah, that might be.
maybe just a trick. Apply a trick, and then ah, they might.
Well, it was working before. I don't know. What did you change? Did you change something? Do you have a new camera or something?
No, I think it's just sensitivity. Some kind of a sensitivity is coming up.
Oh, that looks better.
Uh,
Yeah,
it's
that's
better
not.
now, right?
Yeah, yeah.
So
All right.
now we can increase it. Yeah, you can. I think you have
Oh
a way
well,
to
just as I
make
said
it
it.
whole screen. The whole
Yeah,
screen.
I
Now,
like
can you
to
make
make
it
it
whole screen?
bigger.
Yeah. Oh, it's again when you make it bigger. I think something.
No, no, no.
Uh,
There was a problem there
it's okay,
already.
right?
It is a little bit better though. Just
But
I think
I think the
any
air movement.
whatsoever will.
I switch off the fan. Let me. I have a fan running. So let me switch off that and see whether that helps.
Yeah,
Because the air movement is affecting it. Something like that. It's kind of
very
weird.
cool.
I have not seen this effect before.
Yeah,
So maybe the air movement is affected.
could be a loose wire as well. You might want to check the wires. They're all plugged in.
Yeah, a good point. So let me redo it. I have to redo it. When I move it, it kind of takes off. You know, highly sensitive to something. Yeah. Yeah.
So, based on your notes there, it looks like you're going back over stuff you've covered
Yeah.
previously.
I just want to correct it before I go on so that we don't, we are on the same page.
Oh, that's gonna be
Yeah, I
understandable.
know why slight changes. I had to go back and I think I can redo it, reconnect it. Maybe that will help.
Oh, okay.
At least coming on right there. Okay. I think
Uh,
it's clear now,
that's much better.
right? Yeah. Okay.
Yeah.
I think we probably have fixed it. Let me keep it there. So I said for just a minute, I was going through reviewing our previous videos, but this is what I noticed. So 4D hyperdimensions should be 4 here. It's not 6. It should be 4. Just to put 4-dimensional space. Uh,
Yeah.
and the idea, yeah, the rank 6 tensor. Okay, we are coming to that. So no,
Okay.
I find that maybe quite important. So maybe I don't want to mix up. So rank 2 sensor. Okay, I think I got it here. When we are talking about the rank, the elements. I think we still have something to figure out, but I think we can proceed. Like we find that the rank here, it should be the space dimension, the space number or the dimension, therefore power the rank of the time the number. That's 6. So 4 to the power 6, get 4096 elements in the matrix. Okay. So that is a connection, but instead of for the rank of the tensor, suppose I have rank 2, right? Rank 2 time tensor, and 4D space, I have 4 by 4 matrix we talked about earlier. But when we expand to rank 6, so this is where, this is what I'm talking about, the rank 6 time tensor. This one is like 6-dimensional, almost 6 virtual dimensional things.
Right.
So again, 4 to the power 6 we get. Okay, so what that means is that the time tensor, what does the rank time tensor do? So one of the things, I mean, there are many things, but one of the things, important thing is that at any point in time, right? Suppose I'm going through the timeline. Let's say this is a timeline.
Okay.
And let's say this is the information or information event. Let's say event is happening. So you have the past here, then you have the present here, supposedly,
Right.
and then you have the future.
Okay.
Okay. So at any point in time, the present actually is the scalar time intersecting with the scalar space.
Okay. Well, what is it, a plane?
Whereas,
or?
okay, yeah. So what is happening is that at any point in the future, like what we see is that you see a multi time. So this is a vector time. So you see many things. So this is the vector time of the future. So that's why we cannot see it. We cannot really perceive the future because that's vector time. And that's showing multi things, like multi-universe. So you have many worlds or multi-universe pattern. Okay. So that's what it is. So it is not measurable. We cannot see it. But the vector time, what happens is when from the past, let's say history, intersects. So the history is moving this way. And this is the interesting thing I found. The time actually is moving this way, surprising, from future, because this is the vector time. So it's moving there, and the history is moving continuously. This creates what I call now, or the present, or now. So when they intersect, they collapse, the vector time will collapse. Can you see? Okay. Collapse to scalar time.
Yeah. I see what you're saying. So there's time running from the future and time running from the past, right?
Yeah, that's called history. The time from the past, we call it history. And the time from the future is the
wait a second,
vector time.
Yeah, but okay, and the time running from the future, we call it the future, right?
Yeah. So this is a history. So this is the past. The history we call it past.
You just call it the
past.
This
is called the future.
Yeah. Okay, so yeah, that's interesting. But have you considered like how much time has there been in the past?
Okay, so that's what I come up with, like a video game. I have. I think we will eventually have that.
A better question, Raja, and then how much time is there in the future left?
Oh, see, that's the problem. The vector time does not allow us to really calculate the time accurately. We can project the scalar time. That's what we are doing normally. Suppose I project the scalar time, I say now it is 2024. That's a scalar, the scalar value. Then I project it, I say, so many million years after now, so that's scalar. So we are projecting the
But
scalar
I mean,
into the vector regime.
2024, right? I mean,
Huh?
that's 2000 years after 2024 years after Christ.
80. Yeah.
Yeah,
So if we go
that's
back to the
the
past,
basis of our time. There is, you know, it's after an event that occurred,
yeah,
like many
yeah.
many
Let's
years
say here,
into, like, time had already been up in operation.
yeah. Let's
So
say this is like 10 to the power 14 billion. So we have to
you see the
kind of,
question I'm asking, like, how much time is there left in the future?
yeah, actually we cannot answer it because correctly because we are projecting the scalar time.
That's not an
But the
answer,
question
though.
is,
No. Because you're now going back to the present. I'm just talking about the future. How much
yeah,
time, if you had to
the
guess?
future is, yeah, the
uh,
future is represented by
well,
vector
there's
vector time.
a couple of answers. There's a couple of answers, right?
Yeah.
Either go with the normal view
Uh-huh.
that we all kind of take from physics, which is that there's an infinite future,
Yeah.
right?
Uh-huh.
Or you take a different view and you say, no, the universe is going to end at a certain time, and time will end then. Just as it had a beginning in the Big Bang, time and space began. Will it have an end? Well, we don't know, but we don't believe. Like, if you believe in a big crunch scenario, then you'd say yes, it has an end. But
Ah,
that could lead
that's
to a
what I'm
big bang
coming to.
scenario.
Okay.
So
That's what I'm coming to.
that's irrelevant to the question I'm asking, really. I'm saying, is there, if you go back to your previous schematic there,
Uh-huh.
just go back to the previous drawing.
Okay, 1 minute.
Yeah.
Me, it's kind of hot here, getting hot. Hopefully, it will not fluctuate anymore.
That's fair enough. Yeah. You're no fan anymore.
No, Arizona is a desert, so we are in the hot season, getting to the hot season. So hopefully, it
Yeah.
will not fluctuate. Okay, I think it's okay.
Okay.
I think it's stable.
All right.
Okay, this one. You are talking about this, right?
Yeah. I mean, do you have a point you want to make that
Yeah,
will clarify
yeah,
this, or would you rather that I ask
yeah,
the questions? So you want me to hold
yeah.
off for the questions? Okay, keep going then.
Okay. So what I'm talking about, the future is actually a vector time, right?
Yeah.
So it depends on the what you call the route or the path. The path, the the time takes from the past through present to the future. See that path, how is that path determined? The path is a function of the vector time. So vector time means there are many, many scenarios, right? So which scenario does it collapse to? So I have scenario 1, 2, like up to like n. So what it depends on what it collapses to. So the present is present or now is continuously moving to the future. I mean continuously moving to the future per scalar time, right? So we can only perceive scalar time. We can only perceive scalar time. So suppose I plot the scalar time, it's actual timeline. It follows certain pattern. Okay. Now, but this pattern depends on the collapse. So this pattern depends on how the time vector collapses. Depends on how the tensor or time vector collapses to make it present scalar time. So you have many scenarios. It depends. So that's how the path. So the path will deviate as a function of the uh, collapse and event space. So that's the complex thing. So I can now project it. Suppose I project it here, but it could follow a different path. Totally, at some point it can follow a different path. This is what we call by time loop. So this is where we distinguish the time loops. So let's say this is time loop. We are in a time loop, 1960 to 2040. So in that one, we know what's going on. But I know when I do this, it's supposed to go this way. It's actually went this way, went down. So because of the events that happen, partly because humans could affect it. Humans affected the path because of what we do. It has an effect. So instead of following one path, it started following. So this is the path it should have followed, but it followed this path. So that is quite important because what happens in the next time loop? The next time loop depends on what happened now, which will be a past, which will be the history, and how the future this one collapses depends on that. So it's a highly interactive what you call collapse interactive event that can make it, that can take it to a totally different path. So if you talk about scalar time, yeah, it will go like that, but there's good chance it will follow a different path altogether. And that's, I think, if you go back, you can actually corroborate with the events that happened because anytime in the 1960, 90, there's no way it can go that way. We are convinced in 1980 around that time. There's no way it can go, but actually it did. And that's the reason I went back to the books and blackboard and trying to figure out what is the underlying thing. And then we came up, that's why you have to go back to very fundamentals and then an abstract idea. And finally I came that we didn't know, even during Einstein or anybody, that actually time is not just scalar thing that we think it is. It's actually tensor. And I think it's a rank 6 tensor based on group theory and all those things. That tensor produces many scenarios, many possibilities, and it collapses to one possibility depending on the event that's happened now. So depending on the event now, the future, waiting there somewhere, the time, like I said, the previous one, I said the time is going back, right? Going back and meeting the history to produce a present. This time is a vector time, is waiting where to collapse to. So it depends on now. So it may collapse to this value, it may collapse to this value. And then based on that, the path, the path is going to change. And that's why now how much is going to deviate? We can, now we know this one, we can start plotting and figuring out like in next few years how it's going to change, and we may be able to get some prediction. We can extend it based on extreme value statistics. There are two things. I believe there are two ways of figuring out. Suppose I have the timeline and scalar time. Suppose this. So how do you suppose I know this by 2024? Then I can project it somewhere here or here. Let's say this is the extreme value statistics. That's just projecting based on this. The other one is expectation value, which is uh, probabilistic. Probabilistic. Again, expectation value is not really a good thing because just the average. We may have to use variance. So users normally, uh, normally uses normally uses average values. However, we may have to do our variance will have to be variances will have to be accounted for. So when we do that, we'll see that does it then we measure it like in 2028 or something. What happens? If this one gives a better value or this one gives a better value. So continuously, if we figure out, we can start figuring out what's happening. We backtrack uh, and then figure out what is causing that. What is the causation of that? Is there a causality? So I think that's a much better measure than just extending the scalar value and then say, okay, it's going to either going to have a big crunch, or it's going to what you call the you know uh, or nothing happens. Like non-conformal thing says that it's cyclic. So is it going to be cyclic, or is it going to be a big crunch, or any other type of possibilities? I think we are just based on the scalar, but that depends on the path. So the path that follows, normally we think that this is the time loop somewhere. So let's say this is time loop one. We are time loop, uh, let's say 1960, 2040. So now, then we move on to another time loop 2040 to, may not be exactly 2080, 2080 plus something. We know exactly. So each time the time loop value itself could change. I think it's determined partly because of the comets, like Halley's comet, things like that. So things like astro events, like Halley's comet, may affect it, may affect time loop range, call it time loop range. So what happens is that something, I don't know, consciousness, whatever it is, the background, is determining what's going on now, and then it kind of commutes or communicates with the larger astro thing or global thing, and it says, okay, Earth, this is going on Earth. Now, out in the outer space galaxy, something else is happening. How how they are commuting or how they are communicating, and based on that, it says, okay, the Earth should have gone in this particular path, the timeline, the time loop, but it deviated from that path. So now what happens next? If there are aliens, I don't know whether the aliens are there, but the aliens may be able to see that if they are of higher conscious level, they probably will see that, oh, Earth is, why is Earth going this way? You know, the path of the time, why is it going that way? Things like the events, the sequence of events. So I think there are a lot of things that corroborates with that, what's happening in the world now with the wars and other things. Again, it is it's actually deviating it. And it's counter to our expectation. You know, what I expected in 1980, if I project like Back to the Future or anything like that, that was more exotic actually. Based on the events in up to 1980, we projected, and versus what is happening now, there's a lot of variance. It's totally different. The expectation, well, it should have been totally different. And I need a way to figure out that. And this, I think, this explains this time loop things and how it affects and the time tensor and the fact that the vector time is collapsing to scalar value. But that collapse itself depends on the current events. So it is highly interactive or synergistic, whatever you call it. And that is specific to each part of the space itself. So so now we bring in the space. So now we bring in the space here, how the spatial variation. So now we study the spatial variation. So different part of Earth or whatever. So let's say this is Earth. So what path it follows, what's the path and the time loop. So the path depends on the event, time loop depends on the scalar time. So highly interactive. See that? So, but we are trying to, of course, in physics or in math, anything, we have to separate the parameters. I mean, that's the only way we can figure out. We keep some of them constant, either by idealization or linearization or modeling. We say, okay, temperature is, what happens if the temperature is constant? But actually, everything is changing all the time. But we say, okay, we keep the temperature constant and study what is happening is transformation or whatever happening. The same way, keep the time constant for a period of time and see how the temperature is varying. That's the only way we can study it. And then we try to put them together and find a way to figure out how stochastically it changes. So we can figure out a statistical thing, we can figure out the probabilistic thing, then we put them together and see the stochastical things and see whether it corroborates with actually things that's happening. So if that's happening like you did, with your own thing, that if you do separately and see whether it corresponds to what we observe, what we see actually. So that's the only way we can figure out whether, whether it's going the right path. But I think based on the heuristics I went through, and I have been following time quite closely, and I couldn't figure out why the time will change. Only when I came to the tensor aspect of the time, that makes sense to me. That yeah, the future can change. Although I may say, okay, next year this is going to happen, but but if the deviation occurs, what is the reason for that? What is the causality of that? That's because of this particular nature of the time, which is the vector time says that there are many possibilities, but it collapses to particular possibilities based on the event. So the event will feed. It's like a feeding effect. So whatever is happening now is feed into that vector, and the vector now decides where it will be. will have maximum probability of collapsing to. So I think that's what is changing. And normally we don't expect that to change a lot the local regions that we are in, like Earth or something. But if that deviation is very large, then we have to look. So it will be more like an outlier if you follow the statistics. And why is that outlier happening? I think that I would say the outlier did happen. When I talk about the deviation of the time loop, so the deviation, this is a deviation, it's an outlier of the time loop. So why it happened? And then I looked at it. Yeah, some of the things, the way our mind is, right? The mind over matter. The mind can affect. Like we said, there could be 6 universes. Let's say there are. So the mind, say we have 6 universes. Let's say we have 6 universes. So let's say the mind is here, one of the 6 universes. I don't know whether you can see. Can you see? Okay. 6 universes. So say universe one, let's say just put 4, 5, 6, 6 universes. So the mind is here. The body could be here.
Okay.
So the mind or matter means what is happening in the universe one may be guiding what's going to happen in the universe two. So this interaction, how it interacts, it's an interesting thing. And then we combine with the time loop. Yeah, definitely it can affect that, you know. So I may be in the body, my body may be in the universe two, my mind is in universe one,
Yeah.
but how they interact with each other. And then you take about the whole set of people, and if you can figure out a kind of a scheme or a matrix of the whole people, so everybody has their mind, everybody has their body. My mind may be universe one, your mind may be in universe two or three or four, a body may be some other universe. So each person. Right now, we think there are only 6 universes based on what we did calculation. So it could be anywhere. And so certain number of people, you will have the mind in the universe one. Certain other, if you plot certain people in the universe six and six, so on and so forth. So based on that profile, you have the interaction. The interaction could be quite different. That affects the path through which we travel. So when you want to project it and say it's going to be big crunch, things like that, I think there is an input from Earth itself onto that. Uh, but that's not independent. Earth itself is based on other astro objects, other objects that are outside Earth. But normally it doesn't have that much effect, right? Earth can work independently by itself, a lot of the things. The astro events only happen once in a while. Like we think that dinosaurs existed by some astro event, like some meteor or something fell into the earth and that destroyed or annihilated or at least partially uh, removed all the dinosaurs, extinction, so-called extinction of the dinosauric age. So same way for humans, so many things have happened, but still, I think we are able to reconcile or reset back to normal situation. So many things happen, COVID and other things happen, but we are reset ourselves. So World War happened, we reset. World War II happened, we reset. Cold War happened, we are resetting. And all the things we are resetting to some degree, we are going back to certain norm, we are able to keep that. But the question is whether that norm changes from time loop to time loop. The next time loop, whether the same norm will happen or not, is a big question. So based on that, the path could change, and hence the things like big crunch and everything could could have could be, the outcome could be very different. So there's a possibility of that happening. But how the small thing happens, the big thing is that quantum mechanics says that, fluttering of the butterfly affects the how the cloud is going to, how the rain is going to happen or not. So it's a mix up of cause and effect, of course. But what it says is that how the small thing, an atom, can affect the whole universe. You know, so that kind of thing. So how the small thing can affect the big thing. You know, it probably can. Like there's examples like ant and elephant. An ant can kill an elephant. Uh, because it can go to this tusk or nostrils, and it can, can go irritate that, and the elephant go mad, and that can, cause catastrophe. So there's possibility the small things can affect the big things.
Yeah, good point.
But so that's what probability and quantum is. So what we are talking about a quantum, the funny thing is that if we talk about quantum relativity, it's like discontinuum continuum. There's an inherent contradiction in there. But how, like granular space-time, is space-time continuous? So granular space-time is discontinuous in a continuous thing? Possibility is, but you have to explain that. So that's why I came up with something called, the local factors. I call it tortuosity. It's a measure of complexity versus order. Okay.
Okay. Yeah.
Or the
You have
order to disorder, or order.
you have to move that up a bit so I can see it.
Okay. Can you see now? Okay. Yeah.
No.
So you have disorder or order
Oh yeah.
versus tortuosity. So I can say this is where the stress tensor. So it could be function of the stress tensor, sigma, which is a stress tensor, and disorder order based on the entropy, which is temperature. So now I take a new paper and say, okay, now I can plot. This is where the some relativity and things like that comes back. I'm not going to use. I don't need that to explain that, I think. So I have temperature. Suppose I follow temperature. And I have stress tensor. Sigma mu nu. Temperature T, right?
Mhm.
So I follow this. I should be able to figure out what's going on. So at any point, this is more the local region. So local event is based on the stress tensor, the tortuosity. So for example, we said that things can be quite chaotic, the local center. You mentioned some example of, and I mentioned about the localization event. Um, let's say gravity itself. Maybe it's gravity itself, maybe like that. And temperature, it is electromagnetic. Let's say, okay, which is like quantum form, so to say. It's affecting that. The gravity is affecting what's happening at the local level. So it could be quasars, black holes, or quasars, things like that. So this local thing, this is more global. So you have global thing and the local thing coming into picture. So now we plot it in space. Uh, Now we have to actually plot it based on one thing, 4 HD space uh, times 6 virtual dimension. VD is time, virtual dimension, or rank 6. So this is 4 dimension. So you can see it's very hard to plot it, but I think we need that, to plot this one, and then we can figure out like how it is, whether it is granular. Is it a granular space time? And I question that space time itself, whether we can use the term space time. But is it granular space time? Like it can isolate, a lot of things can happen. So hence, is it then, is that inhomogeneous universe, that sense? So if it's happening like that, isolated, homogeneous, the equation I came up with, I don't know whether I talked about earlier. I believe everything is like superluminar, noisy, general condensate. So that's the entire universe. Like, so, but I can create out of the noise. I have an algorithm. I can write the noise at any point get distorted. So and then creates signal. So this is called a distorted noise locally. Okay? And that helps to create signal, creates like hot PDP mechanism. Now, interesting thing is that this noise becomes part of the original noise, becomes indistinguishable. So these two become indistinguishable eventually, within a fraction of a second. So now I can write the reverse order. I can write noise plus signal, so it becomes indistinguishable. So that noise plus signal creates a new type of noise, which becomes indistinguishable. It becomes, gain goes back to noise. You see that? So only for a period of time it is perturbed. So it's a perturbed system that creates real universe via a hot PDP mechanism, etc. PDP mechanism generating particle spectra. So this is an overall picture I am developing. I don't know whether you can see that. This is the overall picture I am developing, which makes sense. So even it goes beyond quantum, what you call quantum form and everything. It goes beyond that in some sense. But so, which means that all the time there is noise. The only thing is that, so you have the noise, right? So noise, you have evaporation, then you have condensation. So this is the base level of the noise. So the evaporation creates vacuum here in between. There's a vacuum. This is superluminar. And here is the real universe, somewhere here. The evaporation creates a real. So this is the process continuously is going on. But if you look at the overall picture, this algorithm says that, I'll call it algorithm if you want to call some kind of an algorithm. So you can create by perturbation technique, you can create that, and then eventually it goes back to its original thing. So in that process, that's what we are. If we look at our creation, we are born somehow, right? Certain process. But then we perish, we go back, and we become part of the whole thing. So that makes sense even from mythology and our religion and everything. Also, it makes sense, all the scriptures. So I think this picture gives the overall thing, but specifically, look at our earth or something. These things are happening, and we can explain it. Now, we need more mathematics to make it more rigorous, But I think that conceptually, it's starting to make more sense, more sense to me. But you have to work on it. But what I find that for HD space, 6 virtual dimension, that that probably gives more quantification or more justification for group theory and everything. I think we can build a whole model based on that and develop these things and see. What we could see is finally develop the time loop, the model of the time loop, and then see, like I said here, how the scalar time is going to change based on this. So that's how we can track it and see whether our model will, whether a model that you can develop based on this will explain a lot better than what we have now. That's my hope. That's my present, present part of the research. I mean, that's my present thinking. So yeah, I will open to your comments about these or any clarification, things like that. And then after that, probably I can present the next slide. I mean, we can finish our live broadcast, and then I just go over with you our next presentation. Briefly, the PowerPoint of the next History of Physics, Episode 4 presentation. So, Christopher, so you can go ahead if you have any particular comments. So, Christopher, are you there? Oh, something happened? Oh, let's see. Did you go off? Christopher, are you there? Something going on? Oh, you seem to have gone off. Are you there, Christopher? Can you
Yes.
hear me?
Yeah, no, I'm here. Well, can you hear me?
Yeah. Were you able to hear what I was telling?
Yes, I mean, I got some of it.
Are you okay?
Yeah.
Okay.
Okay, so yeah, it's some good ideas there, Rajan. Not
Yeah,
sure if I agree with it totally, but yes, some good ideas anyway.
yeah. This is the concept overall concept I'm developing. Of course, we need a quantification, the mathematics to rigorously analyze this. But and then see how well it predicts. Of course, everything is tested by the prediction. So hopefully, this model we can come up with some predictors. Hopefully, we can measure those predictors uh, and see, as time goes on, whether that will hold up. You know, so that's the way we can figure out. But I think you need about this much, to actually model the stochastic. It's like a stochastic modeling. So you need something
Yeah.
like that to do stochastic modeling. But I think the idea of four-dimensional space
Mm-hmm.
and six virtual dimensional time with tensor seems to, I'll be rehashing again. I know I'll go over and like I said before, self-criticize. I am skeptical all the time, and then question myself whether that's true or not. So you
Yeah.
brainstorm and you are going to hardball all these things, and then you come clear and you go to sleep and come back and
Yeah.
see a fresh view whether you know is this something meaningful? Is this something that is
Well,
that
yeah.
we can
I think,
perceive for?
I mean, based on what we were talking about, wasn't last week we weren't here. Maybe the previous week.
Yeah,
Remember when we had the helical time Mobius strip?
yeah, yeah. You want me to show that?
Well, I mean, do you have it there? I mean, well, so, but I think it was I was showing. I think I was showing some stuff on the screen, and then I was explaining how if you have this linear acceleration beyond the speed of light, you have this helical
Uh-huh.
Mobius strip. But then I think we came to the conclusion there there was some way that I managed to stop the. Oh yeah, was it as you travel forwards in imaginary time,
Uh-huh.
you're actually traveling backwards, isn't that it?
Yeah.
So so time in imaginary space is in reverse in some sense,
Hmm.
and so the forwards and backwardsness
Uh-huh.
cancelled each other out. So we no longer had a helix; we just had a loop, which is
Oh,
what
okay.
we. But then, right?
Yeah, it go. Uh-huh.
So now, so this kind of went back to an earlier idea I had years ago about, and it was going to be a story that I was writing where there was a universe. There's our universe, yeah,
Uh-huh.
and it's on a loop. It's like
Uh-huh.
it's it's you can think of it as a circle or something, yeah. So
Uh-huh.
time is moving in one direction on the circle, but then on the other side of the piece of paper of the loop, time is moving in the other direction.
Oh, okay.
So so there was this idea you had, like, let's say like a portal or like a sword, and you could slice through the fabric of space and pass
Uh-huh.
through to the other dimension, the other world, and
Okay.
then time would appear to be moving forwards in the other world,
Hmm.
but it's actually moving
Oh,
kind of
yeah.
backwards along the inside of the paper.
Uh-huh.
So then when you slice back, like the longer you spend in the other world, the further back in time you go in our world. So when you slice back through the space again,
More like
you
it.
step out
Okay.
and you would step out into the past in our world.
Ah, that's the mind and body, actually. You can describe mind and body to be like that. Like I said, mind could be in one universe, the body could be in another universe. So when the mind and the body come together, then you have this effect that can happen, And then we talk about the whole spectrum of people, each person having their own mind and and each person having their own body. Then now certain set of people will be in the universe one. Their mind is, certain population of the mind will be in universe one. Certain population of the body will be in universe two, and so on and so forth. So they all experience the same thing, right? They are all the people in the universe, the mind having the universe one, they may have very similar experiences, right? Whereas they, the people in the universe four, for example, may have their own special experience. So how that the interaction of the universe one versus universe four, the mind itself, the mind level itself, it's quite interesting, right? I mean, how they communicate, were they able to communicate?
Yeah, yeah. Well, I mean, you could go with this idea. So let's say there's 7 universes. Okay? Yeah, because you have the six universes in a circle. Yeah, like each one's a circle, and then you can draw them out like the flower of life or something. So like the vertices of a cube that are edge on. So you're looking at it from, or the corner. How do you say the corner facing? So you have 6 around the outside, and then 1 in the middle.
Edges. Oh, edge and the corners. Yeah. Okay.
Yeah. So the corner facing
you. Corner face. Yeah.
Well, the corner facing you would be the one in the center, right? If you're looking at a corner, if you're looking at the corner, is in the center. So you're looking at a corner on. Then that would be the central universe, if you like, and then you'd have the 6 other ones are surrounding it, and then there'd be an 8th one, but that would be hidden. But yes, the point I'm making here is that so if you had like, you could have like different chakra points. So there's like 7 chakras, isn't there? So each of those could be its own kind of universe or something. And then, yeah, so you could have, and then the different chakras, I think, are aligned to different parts of the body. So you could have different parts of the body are in different universes. They're not actually connected. And that's kind of goes back to, I think it's a Buddhist idea that, we have our senses, we have our 5 senses, and we think of them as being unified.
Yeah.
We sit around, but if you actually meditate on them, you realize that sight is separate to sound, to what you hear, to what you feel. That's different things. So each of those things could be separated. I think. I remember a bloke I lived with who was he had this idea that your arm could be in space, but like separated by hundreds of millions of light years or something. So I just thought it was a really strange idea at the time. But then when I read about that Buddhist thing, I was meditating on the ideas, and I kind of see the point. If you're talking about different, like the visual, then the sensory stimulus, well, we think of them as unified, but if they are actually disconnected, as the Buddhists.
So you can actually think of the 6 universes, 6 different senses. Each sense is in one universe, in different universe.
Exactly, yeah.
So 5 senses, the 6th sense, we have 5 senses, physical senses, so to say. Then you have the 6th sense, right? Then you can have, like you said, even the 7th or the 8th.
Yes.
which is a higher consciousness. That could be consciousness, and then your soul or whatever is in the eighth universe.
Yes. Yeah.
Kind
Yeah,
of.
yeah. Exactly. So yeah, so there's definitely truth there, and then you talk about a continuum. Well, like it looks like everything's continuous, but then it's also broken up, isn't it? So
Yeah,
then it could
discrete.
be,
Yeah. So
could be
discreteness within continuousness.
yeah,
Something like that, or other way around. I don't know which way it is, but
yeah, and
we
so
like to think of that a smooth manifold overall. A universe is like a smooth manifold, so it will be
mm,
continuous, and then the discreteness is within that. You know, that's why we like to think of, because we cannot think of discreteness outside, like you mentioned about the cube outside the hypersphere, because you have edges, and you cannot explain about that edges. Uh, so it has to be a smooth thing, because the energy, whatever, you try to smoothen it out. So you cannot have a sharp edge
well,
at the
yeah,
edge of
well,
the universe.
the
Yeah,
cube was just I was just using the cube because it's easier to model the cube.
yeah,
Once you start creating a hypersphere, as you saw with the diagrams I tried to create, things get
yeah,
a little bit more complicated and a bit more difficult to
yeah,
visualize.
yeah.
But so the cube was purely just a means of simplifying things. But obviously it's a sphere. Wouldn't work if it's a cube.
Euclidean, yeah.
Cube.
So sphere could
Anyway,
be
so
non-Euclidean. Yeah.
well, I mean, all of these cubes, and technically it's all Euclidean, even though it's hyperdimensional. So go back to some of your previous papers there. You showed
Oh,
some stuff.
so let me go back there.
Yeah, I think one of the points you were making was about if temperature was fluctuating,
This one?
temperature was going up and down, and you kept time constant, or you could keep the temperature constant, and the time goes up and down. I don't know how many pieces of paper did you get through there?
Yeah, I have like 4, 5, or 6, I think. So
okay.
this is one of them. Is this the one you are talking about?
It's not that clear. So this was about dissipated electron.
It's more about gravity. Maybe one before that.
Oh yeah, I think it was a bit before that.
This is a scalar time. I don't think this is what you're talking about. Scalar time and timeline.
Well, you know what? I don't think it was that one either.
That's the one. This one?
Well, actually, you know what? Go back to maybe the first one with the. Oh yeah, that was the one, I think. Scalar time.
Timeline and scalar time.
Yeah.
How the scalar time, the path it follows.
Well, it reminded me a bit of this idea of conservation of just the conservation kind of gauge theories, where you can either move. I hate to say, you can either move around the point or or you change one point, it changes the position of the other point. Right.
Synergism.
Yeah, and then there's another version of that where you could have like a bumpy line like you have there. And so imagine if you were trying to draw a straight line across that piece of paper, but I kept moving it up and down so that it created a bumpy line.
Okay.
Or you could try and trace out that exact bumpy line I made, but because I'm moving the paper in the opposite way exactly, it creates a straight line. Do you know what I mean?
Okay. You cancel out the bumpiness.
Yeah, yeah. So something like that.
Yeah, I do that with the coordinate. You can actually do with changing the coordinate. If you know the equation of this one, you can adjust the coordinate. You get a straight line. This is what I do.
That's true.
I think that
okay,
that's a very good way.
Well, that's a fair point. Yeah, that is interesting. I'd like to see that, but So because
I
that's
have done that. Yeah. Mm.
yeah,
Modeling. I have done
yeah.
quite
So
effective.
I mean, that kind of reminds me of what you're talking about with the tensor. So, like,
Yeah.
let's say we have a 4D tensor, like just a space-time tensor.
Hmm.
Um, so in a 4D tensor, it models how the space deforms, right? Like
Yeah.
whether it's stretched or skewed or squashed or whatever.
Yeah.
And that stretching or skewing of the space-time, uh, the stretching of the space affects the time because the space and the time are linked. Yes.
Hmm.
So if you have a rank 6 tensor with
Hmm.
which is bending time in 6 dimensions, is that right?
Yeah.
No,
Yeah.
no, no, no,
The vector. Yeah. The
no,
tensor
no, no.
time. Yeah.
No, it's bending
The
time
time
in four, it's
in four
bending time in
dimension.
4 dimensions,
Four
but it
dimension
has
space. Yeah.
4-dimensional space, but it has 6 indices.
Six virtual. Yeah. Six virtual time dimension. Yeah.
Okay, but then you won't be able to permute all 6 of them within the same four dimensional tensor, right? You'll only be able to fit.
We form a cell, like your 24 cell or something. So
Yeah.
inside the cell, you have both the space and the time varying. You can have a cell inside of which you have the four-dimensional space and the six-dimensional, six virtual time dimension. You know,
Well, that
four
was just a
space
theory.
dimension.
I was trying to link
Yeah,
up our both of our works. So I had
yeah.
the 24 cell quantum work, and then you were talking, which
Because
was,
you
and then
proved
you
that it has
this
to be 24. You
six-dimensional
proved
time
that.
thing, and I
Yeah,
was thinking, well, you multiply those 6 dimensions by the 4 dimensions, you get 24. But then,
yeah,
we kept looking into that, remember? And by the end
yeah,
of it, we kind of came to the
yeah,
conclusion
yeah,
that
yeah.
it did make sense because, like, if I just have a 4-dimensional universe, like 4 spatial dimensions, I can fit
Uh-huh.
the 24 cell into that, and then we
Mhm.
can use that rotation group, which is like the quaternions or the GL23, and we can just rotate, like, and that has 24 matrices in it, but we can use those 24 matrices to just rotate that 4-dimensional object in place, or we could even use them to just rotate a 3-dimensional object in place. But it just seems like we don't need to posit, okay, we'll take 4 of the, like, we can group 4 of the matrices together and then say those are separate groups. But how do you justify? Well, I suppose that's another thing, right? So if you have the
Yeah,
4 matrices that you're splitting off in some sense, and we say they're all unified in the 24 cell, yeah. But then
mhm.
we're saying, and that's like human experience, if you like. But then we're saying that they're separated out into these 6 different dimensions, which are the different senses, yeah. So there's a unification, and then there's a splitting of some sort.
So each universe could have the 24 cell, right? If there are six
No,
universes.
well, yeah. I mean, that might be another way of doing it, but I'm thinking, yeah, no. I think the point we're trying to make is that the 24 cell is the whole thing,
The
and
whole
then
thing. Oh.
right. So basically, you'd be saying, somehow the human experience of hearing is related to 4 of these matrices. I have no idea how you do that.
Mm.
So it becomes a bit more. It becomes very. This is a bit more metaphysical than,
Yeah,
I think, fully physical, but it's
because
still interesting.
suppose we are 24, 24 times 6 is 144, and they take a square root, we have 12 by 12 matrix. Somehow
Yeah.
that makes sense to me.
Well, yeah. Okay, because so you might be revising the size of the tensor in that case. That's okay.
A 12-hour clock, like a day, like
Yeah,
half day or day clock.
absolutely. Yeah, that's pretty cool. So
So we can associate something. I think it's
yes,
important for physics
well,
to associate
associations
the
are
numbers.
it's the alchemical kind of method, So it's the
Yeah,
original. They're good. It's a good foundation to have, and then
yeah,
you kind of move forward with that. But then there was another thing. Then so you see the reason why I was asking you at the beginning, like how long is left in the future, and how
uh-huh,
much time was there in the past? Because
uh-huh.
and this is the reason why I was asking that question was because with the story I was telling you about with the looped space time or whatever it was, and there's a
Yeah.
universe on the inside of the loop, and one like it's a looped piece of paper if you like,
Mhm.
and it could be a Mobius strip. Like if you were to if you get to the speed of light, you're able to cross over into the inside universe.
Uh-huh.
But if you just have like a wormhole where you could just cross straight through
Uh,
somehow,
like a bridge. Yeah.
yeah, then you'd be
Like
in this
Einstein-Rosenstein bridge, whatever they call it, right?
right. So then you'd be in this
Rosenstein.
backwards flowing. Well, yeah, but the Einstein Rose, yeah, the wormhole bridge or whatever is well, generally they say it connects two different points in the same universe. This, on the other hand, would connect to a
Oh, okay, different.
yeah.
It's the extension of that.
Yeah, it's kind of different because we're talking about this other universe. Now, it might be just
Yeah.
a copy of our universe that's running backwards in time. But that doesn't make sense because
Actually, was it Penrose? Somebody Penrose tile, whatever. It kind of extends that how the different universes. I think one of the YouTube I watched was explaining how the black hole and the wormhole and of different things connects together to
oh
explain
yeah,
that.
well,
That's
there's that
quite
idea
interesting.
that if you have a black
White
hole,
hole.
yeah, and it connects up, that's yeah with yeah that's that thing. But okay, so well, that could open up in a different part of our universe, or
Yeah, yeah.
technically, if we want to conjecture, it could open up into a different universe. Yeah, but I mean, this whole problem with time around black holes and presumably around white holes as well. But it's just the point is that or what point am I trying? Oh yeah, so point is that it's kind of if we ignore the half twist then of the Mobius strip and just have it as a loop, it seems to me
Hmm.
that time would have to start at a certain moment in this universe and
Uh-huh.
be flowing backwards, and then
Oh, okay.
it would have to start at a different point in our or at the same point in our universe and flow forwards, and then at a certain
Hmm.
point, the events of the other universe and the events of our universe would intersect. Yeah, they would
Hmm.
cross over, and then they would pass each other by, and then they would both terminate at the point that they started from, and so that would give like a kind of a countdown on the it could start again
Yeah.
from that point, but if it starts again, then all clocks would have to reset at that point. Yeah, because
Hmm.
otherwise, or well,
Yeah, it's like commuting. See, that's the idea of scalar time. Again, that
yeah.
see when the clocks are not matching, most likely they're in the vector time, you know. But
Well,
when
I'm
the
not
clocks
sure.
then
I
they
think I
collapse
don't
to a
know.
scalar time.
Yeah, I think maybe I mean, it seems to me that you're using this terminology of vector and scalar time, but what you're really talking about, or if you were to use different terminology, you could just express that in a different way in terms of the block universe, right?
Mm-hmm.
So you have a block universe that has the past and the future in it, and then the present moment is like a plane that's moving through the block. Yeah.
Mm-hmm.
Okay. So, well, where am I going with that? Oh yeah, and then so then you
You
have
can go
this.
backwards in one thing, forwards in another universe, and then they kind of match up once the time starts going forward in both the universe, and they match the events together, something like that.
Um, well, no, I mean maybe, but
Yeah, event is a marker of time, right? So the
yeah,
events are marking time.
yeah.
You can think of event being a marker of time, and then so the events are correlating. They're correlating. Then the time can correlate there.
I don't know about that, but well, so it seems to me there's another issue maybe that I was considering, but I don't know. Like, if you have this tensor that is, let's say the Einstein space-time tensor, and it's able to warp space, and because it warps space, it warps time, and vice versa. Then you have this time tensor, and I'm just wondering. It seems a little bit redundant, then, doesn't it? Because
No,
why do you need to?
no.
If you warp space, then you warp time. But then
Not
this,
necessarily. I believe that the only when it collapses, when that vector time collapses, then it commutes with the space,
yeah,
produces a
but I
scalar
think
space time.
if
So
you're
it's
using
scalar
a
space
different,
time.
if you just used general relativity's terminology of a block universe, then you don't really talk about vector space or vector time. And the present moment is just a plane moving through the block, and the future then is just the piece of the block that it's moving into, and the past is the piece of the block that's left behind. Now, I think you're talking about it as something different, where it'd be like uh, like two flows of a river, and where they sort of intersect or whatever.
Yeah,
Yeah, so it's
confluence. I
interesting.
think like a confluence.
Yeah, like there's loads of things that are like that, aren't there? There's
Yeah,
like,
tributary. I mean, they're called. Yeah,
the catenary curve maybe is one where
yeah.
you have a chain and the bottom link of the chain hangs down, but if you lift up one side and lower the other side, the bottom link moves along the bottom of the chain, so it goes from one point to the next. That doesn't really capture exactly. Oh, I suppose it does in a sense, because you've got one thing is going up, which could be time going forward, and the other one's going down, which is like time going backwards. And together
Like
they
the
create
field,
they
like the
create, the
like the
illusion.
Kirchhoff equation. Yeah.
Together they create the illusion of time moving forward or something.
Yeah.
So really,
Yeah, I think illusion is a correct word. I think it's a lot of this illusionary. Time aspect is illusionary
yeah,
because and also that actually corroborates with the vector time also, the illusionary aspect. Why we feel
sure I see
illusionary is
that.
partly
I
because of
think, I mean, you're using like mathematics and mathematical
Yeah.
terminology and objects, and I don't know if it really. I'm not sure if it really. Um, what's the word? elucidates or adds anything to the ideas that you're ultimately talking about. Just doesn't feel.
It tells you. It tells you the deviation, the deviatorial. I call it the deviatorial tensor or deviatorial aspects.
Yeah.
There are a lot of deviation, right? How do you explain the deviation? This one will explain the deviation.
Well, yeah, I mean, but right. I see what you mean there. So, well then, yeah, but that's another thing, right? So let's say you have a time loop, yeah, and then you say, well, look, so you have a loop of time, but every time it loops around, it's different. And is it really a time loop? I mean, well, you could say, well, look at a Fourier wave, a wave that's combined, made of a number of other waves, and each one is periodic, but when you add them all together, they look a bit chaotic or something. So a bit like what Terence McKenna did, where he added all the waves together and you got a repeating signal, but it was always different because it always got smaller and smaller. Or like Philip K. Dick's work, where he talks about time loop. Each time it goes around, it's the same event, but it always looks different. So that's what you're talking about. But now you're saying that, well, not only does everything look different, because it appears like time has moved on, people in the past have died, new people are born, and so forth. Yeah. Not only have the characters changed on stage, but also the story is changing. So does that not indicate that the loop has ended?
No. So the thing is that what differentiates between the past, present, and the future? That's the whole question. What is the key thing that differentiates?
The question is, does that not indicate that the loop has ended? I think that's the question. But
no, the time loop may be ending. See, if you look at the time loop, like I said, 1960 to 2040, I would expect by 2040 or so that person current time loop will end, and then you start a whole new time loop.
I know that, but I'm saying we're discussing whether the idea of the time loop is still in effect. I'll grant that the time loop is probably accurate up to like
2 years.
Yeah, I don't know. Maybe the time loop is still in effect. So it's hard to know. I do like the. I think it would be very, very difficult to prove. I think it would be very. I don't know how you're going to prove it using a tensor.
Yeah, path. See, important thing is the path. The path we take.
It seems a bit too abstract.
Yeah, but when you talk about the path actually has events. It has what you call the fingerprint of the events, whatever you call it. The actual record of the events is the path. So if you
well, then you're talking about like an event space or something. You mentioned
event path,
but it seems to me like you were more kind of where you have the future and the past collide to collapse to create the future. So it was more like a wave function collapse.
Yeah.
So you're kind of linking in quantum mechanics, and that's kind of interesting. Well, and then that connects to Feynman's work where he talks about the particles, the antiparticles. One goes forward, one goes to the past, or even the time. The non-reversible time kind of thing on the quantum scale, and then you have the collapse, which creates presence. So I think that's well-established kind of idea already. I mean, you might be drawing attention to it again, or maybe for the first time, but
in a different way, explaining a different way from the point of view the tensor time and linking it with the aspect of the
okay, but we have to wonder, tensor time. See, we already have we already have a time tensor with the one that Einstein has is a space-time tensor, so time is in there. Now I know it's a scalar time, right? In your sense, you're saying it's just one.
That's the difference.
Thing. Okay, so it can speed up and it can slow down, right? That's it's one-dimensional. It can go up, or it can go down. It's really two-dimensional, I feel like, but well, one-dimensional. Okay, so you have a six-dimensional time, so in your thing, time can speed up. Okay, now how is that going to affect us on the time loop? It's not, because we're not going to notice.
It's Quaternion. There's Quaternion aspect of time.
Wait a second. Just let me finish. If all time speeds up, no one in the universe is going to notice, right? Because there's nothing that we can look at relative to say, oh look, time is speeding up, because we can't see outside of the universe. Yeah. Same if all time slows down, that's not going to have an effect on anyone in the universe. So those two are not going to help. So you have 4 dimensions left. So let's say up is time speeding up, down is time slowing down. Now, what happens when you go to the left, or to the right, or to the front or the back, or because those are you're talking about 6 dimensions, right? So that will be what happens when you move in the 3rd dimension. If you move anywhere along the XY plane, right? How would that affect the time? Because that's what the tensor is going to do, right? It's going to deviate the path off from its trajectory, which would be straight, presumably. It will start moving into a new coordinate system, which has 3 or even 4 dimensions, because you have up and down is actually just 1 dimension. Then left to right would be another dimension. So you would have to describe what's happening when time is moving left or right. What does that mean? Usually if a path starts going left or it starts going right, then it takes longer to reach the projected point that it was going to be at originally. So that's another way of saying time is slowing down. But again, we're not going to notice that. Or in fact, would we? Actually, that would just... Okay, so if it's from a purely subjective point of view, you might say, if I'm looking at my watch and I don't know, I'm at a lecture in college or something. It's a particularly boring lecture.
Okay.
I know the lecture finishes at 3 o'clock, but I'm looking at my watch, and it takes a lot longer to get there. So you could say then, oh, well, time is moving to the left or something. It's
the interesting thing, you brought an interesting thing. Suppose I'm the lecturer, right? Sometimes boring thing. The time CPU drag on. It keeps dragging on. When is it going to end? You'll see, right? Yes. Whereas it's interesting, the time just flies off. You lose it's as if the time is going too fast for you at that time, right? That's the sense you get. That why did it end so fast? The other case, why it didn't end at all? I mean, why is it dragging on, right?
Yeah.
So you have to, again, the time, as far as scalar time is same, like 2 hours, whatever. But that 2 hours, the experience you have is totally different. Just the opposite. You see what I'm saying?
Yes.
Depending on how interesting or boring the lecture is.
But someone else who's also attending the lecture might be sitting beside you. They might be taking notes, and then it might fly by. So it's a subjective thing. So this isn't
probably subjectiveness. Yes.
Yes, this isn't something that we could probably measure with certainly not something we can measure with a clock, because the clock doesn't care about how we feel. It just kicks on. So
exactly,
it doesn't look like we're going to be able to measure with any other kind of device, because all other devices that depend on time just use clocks anyway. So I would say, therefore, that there's possibly no scientific or experimental way to engage with this subject. However,
Presently, we cannot think of anything, conceive of anything at present, but we may come up with something in the future.
Well, that's true. I mean, if you keep thinking about it, you see, a lot of people, I'm sure, I mean, I used to think about this stuff when I was younger, and I think a lot of people who possibly have a sort of misconception of what relativity means, like you see this a lot. If you were to search online the question like, is when we talk about relativity, are we talking about how time appears to slow down in a boring lecture? And you know yourself, like, what's the answer to that? Physicists will say, no, it has nothing to do with that.
Yeah, I also believe that in a way, because the scalar time is not changing. See, I had to qualify the statement. The scalar time is not changing from my point of view. But
right, yeah, no, I'm not saying that you're saying that, but I'm saying that would be, it's like, I'm saying that what you're attempting to do is taking a seemingly very naive question that a child might have, but you're entertaining it.
No, in a sense that, how do you explain that?
This is just my interpretation of your work, but it seems like you're saying, okay, rather than just dismiss that and say, well, no, this is actually what relativity is about. You know what relativity is about, but you're saying, okay, that's fine. But now in order to answer the questions that I have about the time loop, I'm now going to entertain these more seemingly naive concepts in order to flesh them out and potentially produce something that's actually very interesting. So that's fantastic. I applaud you on that. I think you have a long way. I think you've quite a long way to go. But also, I'm a bit confused. There's certain issues that and reservations I would have. I think I brought up a number of them, but really, what I'd be interested in seeing is how does time change under all transformations of the tensor that are upon it. So if you have you were talking about a 4-dimensional tensor, time tensor with 6-dimensional indices. So a rank 6 tensor, but it's still 4-dimensional. So it's basically your time then is no longer 1-dimensional. It is, correct me if I'm wrong, it's 4-dimensional, right? But it's 4 by 4. So you're going to be able to, well, you've got a 1-dimensional line, and then you'll be able to distort that in certain ways, presumably, so you'd have to say, like, well, what does it mean when the line is distorted in the XY plane? What does it mean when it's distorted in the ZW plane? You know what I mean? And you would have to explain what all of those mean. And do they just will they just relate back to I don't know, like different chakras, like, oh, the red chakra makes you angry or something, but the yellow chakra makes you hungry. So when the line goes this way, you're going to feel hungry. But again, that's going back to like a subjective thing, because you might feel hungry.
Yeah. Yeah, exactly.
So then you might have like a permutation then of like your 6 universes and say, well, the people that are feeling hungry are all in this universe, and the people that are, know, and then, but
that categorization is probably a lot better. I think that will explain, that certain people share that same thought. There's a group of people.
Well, that's kind of interesting then, because then you've got a permutation element, but then you also have the fact that, right, let's say you and Emmanuel are hungry, both hungry on Tuesday at the same time or something, right?
Yeah.
But then on the following Tuesday, you're hungry, but he isn't. But now he's, I don't know, now he's out exercising, so he's working his heart, so his heart chakras. So that means he's now moved into universe 5 or something, right? So then you would have another permutation issue, which is that all of the elements in the set are able to permute into all of the different worlds. And so that might give you some sort of very complicated thing that, like, maybe the time loop is how many, you know, like, right, it's it's complicated, but it's got a lot of elements. But if you were to repeat it over and over again, eventually it would repeat. Might take an infinite amount of time, but you would get the same pattern again, yeah. And so maybe that's your time loop. This is kind of going back to have you ever looked into the Mayan calendar and how that works?
Which one? Mayan. Oh, Mayan. Yeah.
Yeah.
They say 2012. There was a big talk in 2012 about the universe ending because Nibiru or something like that. The Nibiru. Nibiru.
Oh yeah. Like well, yeah, that's true. Yeah, Nibiru is still on its way. But yeah.
It just got delayed.
The 2012 came from Terence McKenna's Time Wave Zero, because he made the wave end at that point. But the Mayan calendar, they have a 365 or 360 day calendar. That's the year calendar, and then 4 or 5 days are out of joint, so they don't do anything on those days. They're like a holiday. And then they have a 260 lunar calendar, which is for the priests, like, was a holy calendar. And then, so it's like two wheels, one inside the other. And the day at the beginning of time, let's say, day 1 on the sacred calendar is aligned with day 1 on the profane calendar, I think it's called. And then as time goes on and the years go by, they go out of sync with each other, right? Because one's 260, 360. And it takes like 52 years or something for them to come back into total alignment. I don't know the exact way that it works, but something like that. And so they believe that every time it comes back into alignment, the world is going to end, So they did actually believe, like, technically, if the Mayans were still alive during 2012, still around, they would have thought, like, oh, the world's coming to an end again, And what they would do to prevent that was take all the furniture in their house and drag it out inside and set fire to it, and then they'd start again. And they probably did a lot of other stuff as well, like sacrifice. They did an awful lot of human sacrifice as well to try and stop it from happening, which was, well, I'm not sure about the Mayans, but the other guys did as well. But certainly the Mayans as well, I'm sure. So that was their method of trying to prevent the end of the world. And well, so the point I'm making there is really is just the pattern, the sequence pattern that they had, where it starts on 1, and then it goes out of sync, and it comes back into alignment. So you could have something like that as well, but it's a little bit too, because there's like 9 billion people on the planet. So then if you have all the different states, permutation would be too large, and it wouldn't repeat in a normal. Certainly wouldn't repeat in 80 years. So you'd have to come up with another way of reducing that number to a manageable size. That meant something. So, like, there are 6 types of people. Maybe there are 6 types of people, and then they're all separated. So you have like the 6 degrees of separation or something. is, well, this was another idea I had before, where you have like 6 degrees of separation. This was for a story as well, so it's like there are 6 people that you know, and then the 7th person. Oh no, there's 6 people between you and some other random person or something like that. The 7th person, like the 7th degree of separation, is just you again. You know.
Oh.
But it's a copy of you that you've never met. You know.
Oh, okay.
It's just living out in
It's
the world.
a quantum concept. It's like a quantum concept,
I guess. So you're never going to meet this person. No matter how hard you try, and no one you talk to will have ever kind of spoken to him, or by the time the person gets to talking to maybe the 3rd person, the noise to signal ratio gets drowned out. And if you ever hear about this individual that is your double, by the time it won't mean anything to you. You will just go, yeah, whatever. I'm not interested in that. Like, who cares?
It's like an evil twin. It's like the evil twin type of thing.
Yeah, exactly. But there would be loads. There would be loads of these people, like, on Earth. You know, because you think every 7th person. So what is that? 9 billion divided by 7 or something. Well, I don't know. It would work out some way, like, But anyway, it was just an idea for a story, and then in this story, the guy, the protagonist or whatever, finds out about his 7th self somehow, and then goes to talk to him, and then the whole, like, I never figured out. It's
kind of like, I'm reminded, the snake, it goes back and catches its own tail.
Yeah.
Its own tail.
That's it. And there was actually a movie. It was a movie like that called Being John Malkovich. Did you ever watch that movie? Anyway, in this movie, it's called Being John Malkovich. In this movie, there was a little door or something in an office, or like between 2 different floors. And if you open the door and go into the little room, you're inside this person's head called John Malkovich. Okay, and you're seeing the world through his eyes, and you can, like, control his body and just live the life of John Malkovich for, like, however long you're in the room for. So John Malkovich hears about this and is told to go, somehow anyway, he finds out about it, and he goes up to the room and he enters through the door, and so he's in his own head now, essentially, and he's controlling his own body. And what he sees through his own eyes then is that everyone in the world, like, he's sitting at a dinner table talking to a woman, having dinner with her, and she looks like him. And then he looks at the waiter, and the waiter is him. And then he looks around, and everyone's him. And they're all just saying, copy. Yeah, it's like, it's kind of like a recursive kind of thing or something. And everyone I think they can only say Malkovich. Like, all language is degraded into his name. And and he just feels like he's losing his mind at that point. He's like, and then he runs out of the...
crazy.
It's very funny. So like, that would be the kind of thing, you'd meet yourself, but somehow the universe will unravel in the process of, like, you've broken through a barrier that wasn't meant to be, like meeting yourself in the past, and that kind of thing. If you were to time travel and encounter yourself in the past, that the whole universe would disintegrate or something, that kind of thing. But too much effort to write and no clear.
Yeah, idea. It's like the senses are being pulled apart. It can happen. Then it can happen because one sense is in one universe, another sense another universe. So you feel, kind of distended. What do you call it? Distended? What do you call it?
Or distant. It's just like you feel
you're separated.
Yeah. Maybe. Yeah, I understand. Well, that's it. Okay, I think we did like 3.5 hours there, Roger.
Yeah, but can I just go through? We can stop the live and I want to go through briefly, if
Okay.
it's okay, what I'm going to talk about